the reason that we're here today, Biogenic Specimens V1, Cesar, um, looking at Houdini and Maya, um, is what we'll be looking at today. Cesar, who's our tutor, is a partner at Lima Labs and has an MSc CAD at Zymorphine. And Cesar is a Peruvian architect, graduated from the PUCP, Peru, with expertise in computational design, digital fabrication, and interactive multimedia, holding an MSc in computational advanced design from Zymorphine. He has experience in architectural design, BIM, and parametric modeling. He has taught and consulted at Lima Labs, specializing in Rhino, Grasshopper, Revit, and 3D printing. Currently, he works with simulations and rendering along with interactive multimedia projects. So, right before we get started, just want to remind everyone that this webinar is recorded, and if you miss anything, you will get access to view the recording after the webinar. We will send you an email once that is ready. Please make sure you switch your chat to everyone, you as well, Cesar. Switch your chat to say everyone instead of hosts and panelists. This way, when you're writing in the chat, everyone can see what you're writing, or Cesar, if you want to share links to any files or anything. Um, yeah, we'll hand it off to you, Cesar, if you want to get with it.
Great, Mike. Thanks. I'm gonna upload link prepared with the files today. Should I drop that on the chat, right?
Yeah, exactly. If you have any files, you should
So
drop the link there.
is that
Perfect.
great. I'm starting to share my screen right now. So hey everybody, hi
Yep,
Mike.
we see it. All good.
Yeah, thanks, Mike. So good day, good night, depending on where you are. Well, thanks for the introduction, Mike. But yeah, I'm Cesar Requejo, and I'm from Peru. And I wanted to make a brief introduction first before jumping on Houdini. We guys, uh, we all are on the same page with the concepts that we're gonna talk about today. So, first of all, I wanna talk a little bit about the interest of this workshop. This is an image that I prepared for my undergraduate thesis, but I feel like this represents a lot of what the ideals of habitats and the relationship with its living organisms are. So this is that thesis was about space exploration, and my idea was to take not only the humans but the habitats that surround the humans to space. Like it's not very coherent to just want to take the humans out of its habitat and say that it's gonna do well without the habitat that he was adapted to. So that logic is for all creatures, right? The habitat molds the creature and shapes the way of how it grows. And yeah, and I also feel attracted to these creatures, like the colors, the patterns, that I feel like if we are into starting with this kind of modeling, we should look out to the references in nature, because they are pretty exciting and amazing. And yeah, so also this is an image that we for the masters, me and my partners made, and it has these ideas, right? Like the colors, how the materials work, and uh, try to make a complex creature, not only visually but in the coherence of the tissues. This is another image from another creature, and we can see here like a lot of details as well, like how we by its composition we can kind of understand how the legs work, how the claws work, how these tentacles are grown. So working with a creature, I feel like it's more giving it a story, like to make it more coherent. So we don't want to get a random alien or a random shape out of nowhere, right? We kind of have to make sense out of a model. Like, of course, it doesn't have to be like 100% physically proof, because this creature doesn't exist and probably won't be able to stand by itself. But yeah, in the fiction, we can kind of get the idea of how it works. Like under certain conditions, this creature can work. Like, and that's the story that we have to kind of create to make a coherent creature. So for this workflow, to create this creature, um, Houdini helped me a lot because of the procedural workflows that it has, and it was a pretty amazing road because you can see that it starts from a simple model, and the details are adding on the way. So yeah, this is the road that my partners follow, me and my partners follow. Just wanted to mention the importance of sketching. Like in the sketch, we kind of had the idea of how the creature, how the tissues are gonna compose a creature, right? So we can see like the first claws, the first like the arm, the shell, the head, the legs. So while sketching, I suggest you to do this, like have an idea of how to compose tissues of the creature to so it makes sense. And then you can start modeling a shape and start adding details. Of course, we are not going to achieve like a whole complex animation for today because this was like a 2 weeks work or 3. I don't remember exactly, but it was a long road. And yeah, oh, I also wanted to mention that AI is important, yes, but like when you compare the coherence of this simple sketch, it's of course different. Like this creature doesn't represent exactly what we wanted, so sketching was always more precise for us. So I suggest you to take some time to do the sketching. And yeah, this image I also like very much. This isn't Houdini, but this is ZBrush, and we also did some sculpting. Houdini has its own sculpting tools, but yeah, you can achieve any level of detail on Houdini or ZBrush. This level of detail is achievable, but you have to be careful with the polygons. It's always something you have to look at. Yeah. Additionally, we're going to talk about as well about the habitats that allow the creature to exist. And so I didn't want to focus just on the creature, but also on habitats, and because making a habitat has some kind of different logics, and we are also going to talk about them. Like you cannot make an idea of this creature, like how it works, like its relationship with the habitat. Like this is of course like a creature that protects the eggs and has some kind of relationship with this other creature, right? Like it's looking out to the other creature. So of course in habitats you can also do sketching. This is a sketch that we made for another for the habitat of these creatures that I shown before. And yeah, what we wanted the habitat to do, like, and how it relates with other habitats, maybe like transportation roads and so on. Yeah, this is a result of it, like a render result. This was D5. For the previous images, we made them all in Arnold. Yeah, we used Arnold for this and for this one too. But this was D5 because some for rendering Arnold, you have to take a lot of care with the polygons, and this this habitat had a lot of polygons, so yeah, rendering in D5 was more optimal for us as well. And this is another picture of that habitat. And at the end, we kind of created a whole story of how these creatures relate, because we didn't have just one, but a lot of creatures relating between each other. And this was an important step for us because it allowed us to do not only one creature, but how it evolves and the stages of the creature and what's the purpose of a creature and how it relates, how they relate between them in order to harvest this mineral. So it was a pretty interesting road. Of course, it was in the masters for Morphine, so it was pretty cool. So yeah, let's jump right to Houdini. I am using the indie version, but if you're using Apprentice, it shouldn't be much different. Maybe in the later with texturing, we're gonna have some checking to do, but it shouldn't be much. And yeah, feel free to ask any questions on the chat. I'm gonna be looking at it from time to time. But yeah, just don't hesitate to ask any questions, please. Because I know that the learning curve of Houdini is going to be like super hard, but it's just a beginning, trust me. And but yeah, once you get some, we're gonna go from zero, and yeah, with Houdini and Arnold, we're gonna go from zero. I'm not supposing that you have to know a lot of stuff in Houdini. So, yeah, first of all, when you open Houdini, you're gonna get kind of this configuration, right? This configuration, and the desktop that I am using, like you can check over here, like a lot of desktops. I kind of modified the build desktop, and you can modify the user interface with these arrows, like here are small tiny arrows over there, and here as well. So I something that I like is to have the tree network over here. The network view over here. So with the arrows you can open and close these these windows. And with this tiny arrow as well, you can set a network view. So I set a network view here and the parameters view over here. So I have two windows here. Here is a network and here is the parameters. Okay, so yeah, this is the grid. So to make the first geometries in Houdini, you can just tap, and you are gonna get this menu, and you can set up any geometry here, like you can set a geometry. This isn't a geometry. This is like a container for the operations that you're gonna use. So this is the first tab, the first node that you're gonna get when you want to start creating geometries. So I'm gonna do it again, like you've seen tab and geometry. Okay, so this is all you have to do. Oh, by the way, to navigate in the Houdini context, what you're gonna do is like for panning, you're gonna use the middle mouse button to pan around, and to rotate around the space, you're gonna use left click with mouse. You have to use the left click. And to zoom in and zoom out, you're gonna use the scroll. Zoom in, zoom out, and that's it. The middle mouse button to pan, the left click to rotate, and the scroll to zoom in and zoom out. That's all. Okay. We're already in the to access the geometry node, we're gonna double click it, and we have another empty network. So to make things clear, this is a context in Houdini. This is the OBJ context. If you notice, we are when we double click the geometry node, we are entering in a kind of subcontext, like in a folder, and this is going to be the container for any operations that we are going to use here. So, for example, I can start simple, like I can just bring a sphere and sphere, and this is I mean, it's not relevant which one you bring, but I'm bringing this one, and this is the first sphere that we are okay. Again, here are the parameters for the sphere. Here are the parameters for the sphere. So if you start playing around with the parameters, you can just see that this, of course, affects the geometry, and it does it like instantly, like gonna scale the sphere. And also, you can, for example, move the sphere. Like if I want to move it like two units on the x-axis, we can write down here 2, and the sphere is gonna have its origin 2 units away from the origin in the x-axis. And you can also check that there are other parameters like the height, sorry, the movement in the z-axis, 6, I don't know. And here's the sphere. If you wanna focus on the geometry that you're working on, you can use F to focus on it, and it's here. Also, we can check other parameters such as rows, columns, or we can even check how the sphere is composed. How, for example, here we can see that the sphere is composed of quadrilaterals, like quads, but we can check other options like rows, and we have just sphere made by slices or columns. This is another kind of sphere. Can use it for other purposes, and the orientation as well, for example. And this is another sphere. Also, some nodes, some simple nodes like a sphere allows you to interact with them manually. We kind of just right now we are interacting with them with the parameters, but we can come here and you can see like this kind of gumball geometry or yeah, shape draw, and yeah, gumball icons. Yeah, we can check this and we can see that there is a gumball here. So when we enter this mode, like the gumball mode, what we're gonna do, we're not gonna be able to move around Houdini normally. We have to use Alt. The the interaction is like the same, only you have to add Alt, like you have to keep pressing Add to move around the space in Houdini. So what's the positive side of this gumball, of this interface, is that you can interact directly with the sphere. Like for example, I can scale it up in the z-axis. I can rotate the sphere. I can move the sphere with these angles. I can move the sphere. And you can see that the parameters are being updated as I am moving the sphere. Like check the parameters, I am rotating, and this rotation parameter is changing. So this is a way to interact with the geometry as well. Yeah, I mean you can place a sphere wherever you want. And when you're done, you have to press escape to exit this interface, and there is it, like a sphere made of columns. Also, I wanted you guys to check the geometry spreadsheet because here is in the scene view is where you're gonna have the 3D model. Like you can check the how the geometry is, but in the geometry spreadsheet, you're gonna have all its information, like where all the points are positioned. You can also check other information. Like right now we have just points, but for example, if I want to instead of columns, I want quadrilaterals. I think we're gonna check. No, we don't have primitives yet, but yeah, we're gonna have more information later. But here is also where the famous attributes from Houdini are. In the geometry spreadsheet, you're gonna have the information of groups and attributes. Those are two important concepts that we're gonna check later, very soon, because those are the fundamentals of modeling and simulations and almost everything in Houdini actually. So we always gonna have to take a look on the geometry spreadsheet. So you're gonna have to check the geometry spreadsheet from time to time. Yeah, and I I think that's all for the interface, and maybe later on I'm gonna get other ideas, but this should be it. It's just a simple sphere. You can something I forgot, and I think that we should take into consideration. If we're gonna bring another node, for example, we can use a transform node to apply some transformations in the sphere. I just brought it like the same way I brought the sphere, like with tap and transform. So this is transform node. And if I connect the sphere to the transform node, and like the same way you use Grasshopper. I hope you guys have used Grasshopper sometime, or I don't know, GeoNodes is also a very similar interface. Has also a very similar interface, I think. But yeah, just connect it to the transform node, and we can apply some transformations as well to the sphere. Like we can move the sphere, we can rotate the sphere, and so yeah. But now we have two nodes, right? And what if I want to compare this new node, this new transformation node with the previous sphere that I had? What I have to do is to check this parameter in the node. Almost every node, like 99% of the nodes, is going to have this composition, okay? And the visualization node, we are going to start visualizing the node when clicking um, this button. We click the button and we see what this node does, like how it works. And if I go back and click the sphere, I'm gonna see, I'm gonna check I'm gonna see the previous sphere. And this is a transformation that the transformation operation that I apply to the sphere. Okay. And if we want to compare like the previous version of the sphere, is called template. When a template sphere, we check this pink button. We check the button, and I can see the wireframe of this sphere. And this is a good tool to use to compare previous versions of the model. If we want to stop seeing this wireframe version, we just click on that. Just that. There are also some other options here, like the bypass mode. If you check on bypass, what's going to happen is that this node stops working, and therefore this transformation is not applying to anything. Like if you disable the sphere operation, you are not going to have any transformation, and nothing is going to be transformed. If we uncheck the bypass, the sphere is going to come back. We can also use a freeze option if we wanna if we don't want any changes to be updated on the sphere. Then we can check the sphere how it works with the freeze mode. Nothing happens. I'm starting to if I scale it, it's not scaling because it's frozen right now. Yeah, so those are the if we wanna disable the freeze mode, we just check it and discard it. Okay. And now I can modify the sphere freely. Cool. And yeah, that's all for the interface. We're gonna jump right into some exercises right now. And great. We can start. I have prepared you guys a couple of we're gonna start with. Let me check Check this more appropriate. There's some notes and take a while to process because it's the geometries are really heavy right now. But it's just when it processes, it takes a while. But if it's already processed, so this is one creature we're gonna look later today. So maybe this is not appropriate one to start. Yeah, we're starting with this one maybe. Yeah, and for this creature, it's kind of a virus shape. We're gonna check a couple of starting operations. And I want to start with this one because it has a lot of operations, but it's not. They are not very complex. They are not very complex. Like if we see the geometry too well, we kind of get an idea of how this is composed. And also something to mention is that, for example, if we wanna we don't wanna see the wires from the mesh. We don't wanna see these wires. There are display options as well in Houdini. So you wanna come here on this box, and here you can navigate around like a lot of different display modes. For example, we can go to flat shaded, and the wires are gonna disappear. We're not gonna have any wires right now. Right, so we also have this smooth shaded version. It's so smoothed, like you increase the resolution, but so some polygons are going to get too smoothed. Like for example, this is very polygonal, and in the smooth version it looks like not not so kink. There is not a lot of kink right now, a lot of folding. But yeah, that's it. Yeah, and how do we start? We start with a simple sphere. Like I brought a sphere here, and by the way, if you had any issues with downloading the the files on the Dropbox, please let me know. I uploaded a Dropbox link a few minutes ago, and if you had any issues, please just let me know. But this file is already in the Dropbox link, so if you want to access it, you can just check it. Thanks, Mike. And yeah, so I started with a simple sphere, and then there is a super cool node called taper. So if I bring that taper, for example, here, linear taper node, I'm gonna get another. By the way, I usually what I do is just drag this little circle over here, drag, just tap, and linear taper, bring the node that I want, linear taper, and it outputs already connected. All right. So and this is a sphere that I modify the radius, like to have this kind of X shape. All right, and I use linear taper to give it an even more X shape. So, how is linear taper used? And what I suggest you guys to do is to first, with linear taper, press enter. Enter. Yeah, you're gonna get this box. If you use this, and this is going to be like the same that the same idea that when you activate this handle, this combo, you're gonna have to use Alt to navigate the Houdini environment, Houdini space. You're gonna have to use Alt. So you navigate with pressing Alt, and you can also interact with these geometries. Like, for example, if you wanna click on this one, you can make it smaller and smaller and smaller, and the sphere is gonna be modified. You can drag down the mouse, and the sphere is gonna get modified. Or you can drag up the mouse on this one, for example, and you get a completely different kind of sphere. I mean, it's up to you. Or you can also use the parameters. All right. So also something important to mention is that you can check the instructions over here. Something that I like very much to use is the fit capture option, and you can press N, and the box gets automatically shaped on the size of the sphere. Like it becomes a bounding box. And also you can move this second rectangle that controls the shape of the taper. All right. But and when you're done, you just have to press escape, and the taper is done. Also, something really cool to mention here is that Houdini, for example, if I bring a box here, something pretty cool to mention, and if I'm going to increase the divisions so we can see 5, 5, and 5. We have a box with 5, 5, 5 axis divisions on every axis, right? So, and if I connect the box to the linear taper, the box is gonna get the same operation applied. So that applies to anything. Like this is the idea of a procedural workflow is not holding an operation directly on just one geometry, but you are creating an operation and applying to the geometry. But it's not exclusive. Like this operation is not exclusive to the sphere. So that's something very important to notice. So yeah, I taper this sphere, and then I use this node called soften normals. I don't recall exactly why. I don't know if it's yeah, it's gonna be important later, because and if you check here and here in the display normals options, you check, and you're gonna have access to see how the normals are built on the sphere, or on the geometry that you have. And with soften normals, you can check before soften normals. Some normals are acting kind of weird because I don't know exactly why, but Houdini sometimes does that. Like this looks like a broken normal, but after soften normals, the normals are fixed. Yeah, this is pretty straightforward. It doesn't do much, just soften the normals. Yeah, and this is also a very important note. We're gonna start with the concept of groups. All right. Grouping is extremely important in Houdini. You can do a lot of stuff with grouping, okay? The first thing that we're doing is here is grouping some primitives, some polygons. In Houdini, primitives sometimes means polygons, but sometimes it can mean curves, sometimes it can mean yeah, primitive has a lot of variations actually in Houdini. But yeah, it means polygons right now. We have grouped some polygons by its normals, which means I can set a direction. I set a direction here, which is the one in z-axis. Z-axis, right? Yeah. Z-axis positive. I disable the grid. So you can enable or disable the grid with this button. So yeah. This is the one. This is one vector, right? Like the z direction. It's one. So I set one over here. And which angle is going to be spread? Like I can increase this value, and more polygons are gonna be selected. Why that happens? Because a spread angle is kind of a tolerance. Like you can say how precise you want this direction to be. Like yeah. If you want just the polygons that match this normal, you can reduce this to 0, and you're not gonna get any polygons right now because no polygon matches this normal, right? So I think it's 70.1, yeah. So we can keep this one. And yeah, also now we wanna apply extrusion, but only for this group, only for group 3. All right, only for group 3. We do not want all the polygons to be extruded, just the polygons in group 3, right? So I'm gonna bring the poly extrude node. I'm gonna bring the poly extrude node, all right? And I'm gonna start playing with this. For example, I can increase the distance of the poly extrusion, but yeah, we can see that every polygon is being extruded, right? So all polygons are being extruded right now. But if we want only the polygons in group 3 to be extruded, what I want to do is come to this group area over here, this group option, and I can check this tab and check on group 3, right? And now only the polygons in group 3 are being extruded, okay? So you can see right now that only these polygons are being extruded, okay? Not every polygon. Sure, and this is very important. A lot of most nodes in Houdini have this group tab. For example, linear taper, if you noticed, has also this group option. Soften normals doesn't have it. We're gonna dive deeper on the group interface later, but I just wanted to start with this kind of grouping. All right, and yeah, this is the result of the poly extrusion. And there are actually two ways of extruding. Okay, there are two ways. The first way is to is to um, is to extrude the polygons with all connected. But there is another option to extrude with to extrude them individually. Okay, so right now each polygon is being extruded by themselves, like separate them from each other. Also, there is an option to extrude by the primitive normal. Like, remember that we have primitives. I told you like that the primitives are sometimes means polygons, and in this case it means polygons. So the primitive normal is the average of these normals, right? Like, it has a lot of normals, and there is an average. So each primitive is going to be extruded by the average of it. But there is also another option to extrude according to point normals. So right now it's not taking in count the average of the normal. Like, if we click on point normal, for example, this one is extruded a little bit less. And yeah, these ones are also being extruded in maybe a slightly different direction. But you have to take in count that these two are two different ways of extruding. I say this because I want you guys to understand that normals are very important in extruding. For example, in Rhino, or I think in Blender too, you can like just drag um, or set a normal directly, right? But in Houdini, you have to set the normals manually. Normals right now were created by default. For instance, if I bring the sphere, the basic sphere, so it comes already with normals, right? Right? Yeah. So it has normals. But what if we want to extrude in a specific direction? For example, I extruded this shape specifically in this direction. What if we want to extrude in this direction, right? This extrusion was applied, but it's extruding all over, like according to the normals of the sphere. But this shape, like a spaceship, is extruded in the Z direction, right? So to extrude this shape in the Z direction, we're gonna set the normals to the Z direction. You can see here these normals are different from the other ones. All right. So if we want to set the normals to this direction, we have to use an attribute wrangle. And this is going to be the first introduction to coding in Houdini. it's super simple. So don't be scared of these nodes. The wrangle nodes are very important because it allows us to simplify some operations that otherwise in Houdini would be would require more nodes or yeah, sometimes it's easier to do it like with a rank. For example, if we want to set normals, specific normals, we're gonna have to use a simple vex code, okay? So to modify the normals for this polygon, for this shape, we wanna first of all call the attribute normals. How do we call it? We just use this @ sign symbol and the n. This @ symbol is referencing an attribute. It means that it's always gonna call an attribute. We can create attributes with this symbol. We can modify attributes with this symbol. You can do all kind of attribute operations with this symbol, okay? And the n, please remember that is caps n. You have to, so vex differences, caps, and the small letters. So you have to be careful with that. And yeah, so right now we're calling like the normals, the normal attribute, okay? Are we gonna say to Houdini that we're gonna set the normal to this vector 0.04, sorry, 0,0,1. So this is the vector 1 in the z direction, okay? So what we're saying with vex right now is that we're gonna set a normal to this vector, and vector is always are always represented with these brackets. Well, not always, okay, but for this case, it's useful for us to represent vectors this way. And when we're finished, when we're done, we use this this. I don't remember the English name of this symbol, like semicolon. I don't remember, but yeah, we're done, and we just click outside the node, and that's it. All normals are now in the z direction. But this isn't very useful for us because these normals over here are also being changed. But we don't want these normals to be changed. And why not? Because right now these normals are inverted directly into the sphere. Okay. So we're gonna do what we have done before. We're gonna go to group and we're gonna change it to group 3. So right now we are only applying this operation to group 3. Okay, and that's how we can change the normals just for these polygons and this direction. Right now to do this poly extrude operation, we're gonna go, for example, I'm gonna bring another poly extrude. Right now, if we're gonna poly extrude, if we wanna just use these normals to poly extrude just these shapes, we're gonna go to group 3, and the normals are not being applied, right? It's kind of ignoring the normals right now. It's creating the normals. And why is that? Because the extrusion mode is in primitive edge normal, okay? So we're gonna come here, use point normal, and instead of pre-computing the point normal, we're gonna change to existing. And right now, the extrusion is being applied just in that direction, okay? So this is what happens. That's it. And that's how we can extrude just in this direction, okay? But there are also other considerations. Like, what if we don't want to just extrude, but for example, we want to inset? So this gives us an insight on how are the what the possibilities are with the poly extrude node. So I can go, for example, to increase the divisions of the extrusion. Now, here it's only one division, but I can increase this divisions parameter to 10 divisions, for example. And then what I can do as well is go to spine control and play a bit with the thickness scale. For example, I can play a bit with the thickness, like specifically the thickness ramp. Okay, I can make the ramp smaller on the end and thicker on the middle. Okay, so this I am just adding these controls just by clicking the ramp. Okay, just click the ramp and start adding controls, and you can have different kind of shapes. This is pretty fun because you can get all sorts of shape just with one node. Okay. So I disconnected the poly extrude node just by shaking the node. So that's pretty funny in Houdini. So be sure to not shake the nodes too fast. So yeah, and you can play around with the ramp, and that's what I did here. I just played a bit with the ramp, and but also with this value. If you want to increase the value, you're gonna have like a thicker extrusion. So yeah, use this node like in the best way you want. So up to you. Later, what I've done, also the same logic, group by normals in the same direction. I grouped some polygons in the C direction with this spread angle, and something super important here. Okay, we're gonna play a little more with the groups. We're gonna do some fun stuff with the groups because grouping helps us access some other features. For example, I use this group expression now. Okay, what this group expression does is I'm gonna bring another node. We can use code. We can use some Vex expressions in this parameter to group certain polygons. Okay. For instance, there are already some pre-built codes. For example, if we wanna go over here and check this 30% chance of grouping, so we have this code. And right now it's not grouping anything, but if we want to start grouping, we have to check. Click this function which creates parameters for this expression. Okay, so if we click this one, it creates a parameter, and I can start increasing. I can start increasing the values of this expression. So yeah, expression. So I wanted to show you guys this because this has already a lot of pre-built codes. So just for example, we can already modify some codes. For example, I right now I brought the within radius 1 sphere of origin. Like it just groups as the geometries with that are inside a sphere of radius 1. So, but if we want to increase the range, we can modify this one. For example, instead of 1, we can modify it to 1.5 and select more polygons here. Yeah. Also, what have I done here? I grouped only the 3 polygons, the meshes that are triangles. All right. So I just group the triangles over here. Okay. Because later I wanted to make some intersection operations. Like from this group, I want to separate the triangles from the quads. From group 4, I want to create 2 groups. One group that is made of triangles and another group that is made of quads. And you can see already that we have some triangles and some quads. Quads and triangles, right? So I want to separate this with group combine. So I call this group a split, by the way. The groups of 3 vertices, which are the triangles. And you can check this one here, right? The triangles. You just click it and it's gonna return this code. So I wanted to extract first the triangles with group combine. What this group does is, and we name the group. So I named this group 3 because of triangles. And I told the node that I want this group to be equal to group 4, right? So for example, if I bring another node, group combine, I'm gonna call this group triangles. I'm gonna also make it equal to group 4, and I'm getting exactly the same group as group 4, meaning this new group called triangles is exactly the same as group 4. Okay. Then I can apply some operations to the group. For example, I can intersect it with the group called split. Intersect it with a group called split. and it returns only the triangles. Why is that? Because in the split group, we just selected the triangles, and we are intersecting this group with group 4, right? So we are getting, so we have two groups, and we intersected them to extract just the triangles from group 4. All right. That's what happened here. I also we can instead of intersect, we can subtract, and we are getting the quads from group 4, right? So that's what happens. Okay, we use group combine to extract only the triangles. And why why extracting the triangles? We're gonna know later. Yeah, I think I use this for later purposes. But yeah, never mind. It's gonna be useful later. Also, I use polyextrude node, the polyextrude node, to extrude just the polygons from group 4. Okay, so in group 4, in the group tab, I just grouped. I selected the group 4, and I could start playing around with this expression. Also, remember, I changed this option. Instead of connected components, I changed it to individual component elements. Sorry. And also, as I told you guys, we can use the inset, this inset node. Sorry, inset parameter. So these polygons are being kind of inset, right? Later, I use this group attributes from boundary. What does it mean? Yeah. First, we have to activate this option. Okay. I'm gonna bring another polyextrude now to show you guys that by default this option comes unchecked. But if we check it, what polyextrude does is creates a group for us. The group is called extrude front. And what is it grouping? I'm gonna bring another group node. And in this group node, I can use a base group. What's gonna be the base group? Extrude front, okay? And right now we are checking that these faces are being grouped. Like the exactly the ones that are in the front of the extrusion, right? The ones that are in front of extrusion. So that's cool. Later, I used group from attribute boundary to group the borders of the extrude from group. Okay, so what this achieves, um, is that I am getting the borders of the extrude from group. Okay, and I think maybe this we don't need right now. Maybe later we're gonna need. we're gonna need it later, but we're grouping just the borders. Also, we're using another poly extrusion, and we're extruding the extrude from group, same way we extruded previously, with 4 divisions, by the way. And the ramp also, it's modified to have this kind of shape, because if the ramp is unchecked, this is gonna get this boring extrusion. So I check this ramp to get this kind of curvature inside the extrusion. Okay. So I brought back this group. Okay. So I don't want to get into. Let me check which path is more appropriate to check. Yeah, but well, this is the base, okay? And we're gonna start adding some details to this kind of virus shape. We're gonna start adding some details. So I wanna check first which detail is more appropriate. Detail would be more appropriate to check. Yeah, let's go ahead with this. Yeah, this we're gonna check later, but we have to check it right now. Yeah, I'm checking it. Group 1. And yeah, I do remember now. Yeah, if you check this group combine, what this group combine does is just grouping the faces that are quads. So for example, these interiors are not being grouped. And why have I done that? Because I'll call it just for a second, because yeah, base group 1. Oh yes, here it's extrusion. Yeah. All right. So we are just extracting with this group combine just these interior faces, okay, that are just quads. Because if we want to group from here, for example, and we want to group just the extrude front group, we're gonna get the triangles over here and the quads as well. I think 2 of them combined. And how we're gonna extract just the just the quads and not the triangles. It's the same logic that we applied before. we create a group that is just quads. We're just creating a group of quads using the group expression node, using this quad expression. Remember, there is also a quad expression with a group expression. And then we are combining. Like we create a new group called base, and we say that we want the extrude front group, but intersect it with group 1. So it does get us just exactly precisely the quads, not the triangles. Okay, that's it. We get the quads, and yeah, this doesn't do anything yet. We'll check it later. And also, I wanted to extract the quads because later I want to start expanding this to get all of these elements. How do I do that? I can bring a group expand node, and use this use the base group that we just created. We created a base group, remember here, it's called base. We created a base group, and we can start using this parameter to expand the group to the surrounding polygons, surrounding primitives. We can start increasing the work. The grouping. So it expands what its name says. So with 5 steps, we can achieve a grouping of these elements. Okay. And also, remember we had a try group, like previously we created a try group with the triangles. We separated them in quads and triangles. Okay. Also, we're expanding the try group. We're expanding the try group 5 steps. So this is what these two nodes are achieving. One grouping of these elements and another of these ones. Later, we can subdivide, but just the polygons from the group expand 1. Okay, we're subdividing just these elements. Then sometimes maybe this doesn't serve too much purpose. Instead, we can paste here, and this does work. Yeah, doesn't matter. This group doesn't matter much. Sometimes I just create groups to reference between them, but it doesn't do much. So we're gonna get back to this one. Okay. What I am doing here is expanding the base a little. So I am expanding the group base. So remember we had a base group of just the quads. It's the same one here. But now this group is subdivided. All right? Subdivided. If I want to start expanding this group, I get a a better shape, like not a tiny one, but a more circular and bigger shape, because it's subdivided and the polygons on the surrounding areas are more subdivided. Also, we extract the boundaries from this group, extract them, and we extract the curves from that group. So we group from attribute boundary. We're using as a base the group expand tree, and we are getting the borders of this group. And to convert these borders into curves, we want to use edge group to curve. Okay. And these circles are useful for us because those are going to be the basis for these tentacles. Okay, these are going to be the basis for these tentacles. Yeah, today we're gonna check different ways to make tentacles. Okay, so this is a start. So this is a complex, kind of a complex operation, because we do not want only to we could have done here as well is to if we, for example, if we can use a blast node. We can use a blast node and blast the group expand 3. What the blast node does is it deletes the selection. We're selecting here to blast, to delete the group 3, the group expand 3 we created. But we can check this option, which deletes the non-selected. So it does the opposite. I am blasting this to show you guys that there is an option, poly extrude, these shapes, but it doesn't achieve a tentacle shape option. I mean, we can go to spine control and kind of shape this 3. Yeah. Yeah, it gives us a kind of a broken geometry. And why is that? Because this is a base kind of has a plate shape, right? It's kind of plated. So if we start extruding this, it's gonna result in this. It's not getting us a tentacle shape. So, and this is pretty differently, right? And this is pretty different. This gives us exactly a tentacle shape. I mean, we can get a more natural shape, maybe, if we yeah, never mind. We're gonna check how to use this later, but and this is another process. All right, and we're extruding these curves that we extracted in the normals of the base polygon, right? Which is this one. We're extruding these circles in the normals. Okay. Cool. And there are many steps for that to achieve that purpose. First, we need to blast these groups, the groups that we need the tentacles to be on. All right. So these are the base. So we blasted the base, and yeah, do we need the normal right now? I think we don't need normal. Sometimes I just get too excited with the normals, but we don't need that normal. Yeah, yeah. So we blasted the base, right? Okay, and later this area we're gonna check later. Let me check what this achieves. Yeah, we're gonna check this later, okay? Because these are we haven't checked attributes just yet. We have just checked groups. So we're gonna get into attributes later. But yeah, we extracted the centroids from the base group, okay? And we want to project them, to project the centroids on the normals. Oh, sorry, on the primitives, on the polygons. Why is that? Because previously these centroids didn't have a normal. If we project them to the primitives, now these centroids have a normal. Okay. When we check this option, import attributes from hits, we wanna import the normal attributes. Okay. We wanna here we're gonna have to check two options, I think. We have two options to check. The first option to check to get the normals is instead of the project race as method, we're gonna have minimum distance method. Yeah, that's cool. And then we import attributes from hits. And those two options give us the normals for these points. Okay. And that's it. That's how these points have a normal. And why do we want these points to have a normal? Because, oh, sorry, this one, I'm also gonna bypass it. Because with a copy to points node, we're gonna copy this line in the direction of the normal of these points. Sorry, of these points that we have just created. For example, if we have a line, okay, we have a line, and we just copy two points. Copy 2 points. We copy these lines into these points. What we're gonna get is this. Because this line already has a direction, but these points don't have a normal, right? Here previously, these points didn't have a normal. So when these points don't have a normal, they are just gonna assume that you're gonna that you want to import the normal. No, it's gonna assume that the normal is the same as the world. Like you're just gonna have a moving operation, right? So basically this line is being moved to these points. Okay, it's not being rotated, it's not being reoriented, it's just being moved. But when we have normals stored in the points, this line is in the wrong direction. So if we have this line in the C direction, now this line is being rotated, is being reoriented to the points normals. Just because these points have a normal stored, created previously to the copy to points transformation. Okay. So that's going to happen. That's why we need the normals to be created, and that's why we need this operation of projecting the centroids to the bases. Okay. Next, I am using a group expression node to. I'm using this group expression node to create just the starting points. So sorry, to group just the starting points of these lines. Because we need these points because we wanna give this tentacle shape to the points. Okay, sorry, to the lines. This is pretty useful. Oh, by the way, these lines have many points. These lines have many points because I use a resample node. Because I use a resample node. At the beginning, this line only has 2 points, but with the resample node, it creates as many points as we have between these lengths. And so every 0.05 units is going to create a point. Okay. So that's what the resample node is used for. And that's why we have many points on this. We activate the visualization of the points with this option over here. So we can see that we have lines with many points. Okay. And with this group expression, we group the starting points. And this group expression is I think it's first point of primitive. I'm gonna double check this right now. First point of primitive. No. Oh, yes, it is. It is. Yes, it is. It is, but if we're using first point of primitive, right? But right now, it's selecting all the primitives. But why is that? Because we do not want primitive, we want points. So what we have to do is we go to the group type, and instead of primitives, we check points. So we can also tell the nodes over which geometry we want it to run. So right now it's run. Previously it was running on primitives, but we want to run on points. Okay, so it's only selecting the points of the curves. Okay. Cool. So I expand the points just 4 steps. The same previous operation that we have done before. We use the group 1 as a base, meaning we have these groups as a starting points, and we start expanding from group 1. Then I brought this mountain. This kind of noises that applies a noise on the curves. Okay. So I'm bringing another mountain here to for you to check. And so there are a lot of options over here. Okay. What I always do with this mountain group node, sorry, is uncheck this fractal operation, because it's pretty useful. Okay, but for example, so to make a better visualization for it, I'm gonna bring a grid. I'm gonna increase the rows and columns, maybe higher, maybe 500. 500 and 500, and I'm gonna bring a mountain node, and this is what mountain does. Like applies a displacement over a geometry. And if we uncheck the fractal option, what's going to happen is this. Like, it's not going to have a lot of detail. I usually check this because this takes much it takes too much time to process. So at least for this purpose, I don't need the fractal option. Okay. But also notice that every point is being moved. Okay. So we do not want that. We created this group expand specifically for these points to stay where they are. Okay. So we're going to use a little expression over here. So if we tell the group to run over group expand, it's going to run only on these points. And the surrounding points are not going to be displaced. Okay. So how do we tell the mountain group to run over all the other points but this group? We use the exclamation symbol, and it's going to run over the other points but the ones from this group. And that's what I made here. Also, you can play a bit with these parameters. For example, I changed the amplitude, I changed the element size, I changed also the noise type, and it's up to you. I suggest you guys to play with it. And then I smooth it a bit. Also, you want to have constraint points, like points that you do not want to be moved, because smooth is going to smooth everything, and it's also going to displace these points, but we do not want these points to be displaced. So we have this group one as a constraint point option, and as we do not have any boundary, we just want to have constraint points. I checked none here. And yeah, you can play around with the strength of the smoothing operation it's gonna run. I kept it in 3.6, but you can smooth it at a higher value. It's up to you. Okay, and let me check how to. So yeah, we right now have the two things that we needed to make a loft operation or a sweeping operation, right? We have we have, how is this called? We have the profile, we have the profile, and we have the array. right? We have the profile and we have the array. Yeah. Now we're gonna have to do some extra operations to for them to match, okay? Because if we want to use the swap node directly onto them, like this is the backbone curve. The lines, these lines are going to be the backbone curve, and the and these profiles are going to be the cross sections. Yeah, this is gonna happen. This is what's gonna happen. We're gonna do some crazy stuff, but we have to come here and yeah, we have to check some options relating to the construction tab. So there is an option that helps us choose cross-section primitives by attribute. Okay, so we can use attributes to match the sweeps, like because right now it's running all over the place, right? It's not running the way we want it. Yeah, it's running crazy. It's running pretty crazy. That's why we need these operations, okay? I'm gonna tell the operations I like them. So what's the first operation? In the construction tab, we selected choose cross-section primitives by attribute, okay? In the swap node. So there needs there is an attribute that we need. I chose this attribute, the ID attribute, okay? But we have to create this ID attribute. And I use this expression. I at ID equals primnum. I am trying to remember if I need this I. No, apparently I don't need this I. No. Yeah, I don't need it. Yeah. And now I am asking myself if I am. Yeah, it does run. It doesn't run. It doesn't run. Yeah. We need this attribute to be created, okay? The ID. What this does is, and previously in this primitive wrangle, also remember right now we are in a primitive wrangle. We created an attribute with this primitive wrangle, but we needed to run over primitives, okay? Run over primitives. So what this expression does is that according to the primnum, which is like a way that Houdini has to store to identify the primitive, we can check it here, display primitive numbers in this option. We can check that Houdini has this has stored these numbers. How they are sorted, because they are not sorted randomly. Houdini has every primitive with its own code, with its own number, right? So it does have like inherently But what we want to do is fetch this number into an attribute. So we fetch this number with the primnum function, or yeah, with this name, with this code. And we create an attribute called ID to fetch these values, okay? So we are fetching the values over here. We are creating an attribute called ID, fetching the primnums. The primnums are these numbers, okay? Like previously, this attribute didn't exist. Oh, by the way, I can navigate through all the attributes clicking on this option. Like these are the point attributes, these are the vertex attributes, these are the primitive attributes, and these are the detail attributes, okay? But yeah, we can have the primitives. Okay, sure. So cool. We created the ID attributes, right? Then we also want to create these attributes on the profiles. So we brought another primitive wrangle to run over these curves and create the same ID attribute. So that's cool. And what are these funny looking nodes made for? Check if I deactivate these nodes, this is happening. This is a funny stuff in Houdini. Also, please remember that I am using this ID attribute as a cross section attribute over here. Okay, just write down ID. Okay, something funny that Houdini does is that if you wanna sweep a curve, if you wanna sweep a curve over another curve, we want to swap a curve over another curve. So we want to swap this curve over this curve. It's not going to be a straightforward operation. First, what you want to do is move these curves to the origin, meaning you have to move these curves over the 0, 0, 0 point in space. Okay, so to achieve this, I use this loop operation. I use this loop operation, okay? So for example, if I deactivate this, that's why this funny thing happens, because these curves are not being placed in the center. So after the looping, all these curves are placed in the center. Those are all over here, okay? Well, how does this work? For each primitive, because we're running this over primitives, okay? So we want all the curves to be placed in the center. So we connect the curves to the starting start node of the loop. Okay, nothing happens. Of course, nothing happens because there is no operation inside the loop. We use match size, and that's it. We just use match size because match size justifies centers any geometry to the point that you want. For example, we are targeting the position 0, 0, 0, right over here. But if I move this, oh, sorry, I think I forgot to mention as well that if I press the middle mouse button on the parameters, I can, and I drag the mouse over the left or the right, I can also displace this parameter. Okay. Yeah, cool. Yeah, and that's it. As simple as that. Loops might seem scary at the first place, but we need them to run over each primitive, because if I just match size out of the loop, what's going to happen is this, is that all the curves are going to move together, but we want each curve to be moved independently. And that's all the steps we need. Like if I bring another sub node, for example, if I bring another sub node and I use ID over here, and that's all the steps we need. But yeah, also something that I am missing is that by default, what's going to happen is this, right? Like, it's not going to be exactly oriented in the way that in the way of the normals of the lines of the. It's not going to be exactly oriented on like a pipe, right? It's going to be like flattened. So to fix this, we're going to go to tangent type and we're going to use z-axis ignore curve. And that's going to make it, that's going to fix it. That's it. Also, there is this option on the scale tab. Just apply scale along curve, and we're going to have the option to use this ramp to modify the scale of the sections, and you can play around with the ramp, like to get any shape you want. So that's it, and that's how you get these beautiful tentacles. We're gonna have other options later on how to build tentacles, but we're gonna check that later. Also, getting back to the attributes that we left over here. We left this for the end because if you check right now, all the tentacles are in the same all the tentacles are in the same size. Like they all have the same size right now. Okay. We want to have a differentiation. It doesn't look so natural right now because it's all the same size, and if we want to make it more complex, like as in nature, having same size for everything, it's not so. It's kind of uncanny. So that usually happens in hard surfaces modeling, and yeah, but in nature is more organic modeling. You kind of want to have differences. So we're gonna. That's what attributes are needed for. Okay. For example, we can we can we can have different sizes of tentacles depending on the size of the base that we fetch the points from. Remember, we fetch the points from these polygons. We fetch the starting points from these polygons, okay? So we can measure the area of these polygons using measure. And this area, the area of these polygons, you can see here that area is being computed over the primitives. using the area of these primitives, we can make a gradient of sizes. Okay. And how do we do that? First of all, of course, we need to fetch the area using measure. And then we can use this attribute remap. Because areas are pretty tiny right now. Areas over here are pretty tiny. Oops. What have I done? Areas over here are pretty tiny. Yeah, you can see here that areas are super tiny, right? Super tiny. Oh, sorry. Yeah. Also. Yeah. Also, in how would I put this? This measure is being applied only on the primitives, right? It's being applied only on these primitives. But we extracted, if we extract the centroid of this, if we extract the centroid of these primitives, we're running over primitives. We're extracting the centroid of the primitive. We're not gonna get the area attribute. Why is that? Because it is being stored on the primitives. And if we're extracting centroids, we are not going to have primitives. We're going to have points. Okay. So we're going to extract also we're going to transfer the attributes from the primitives to the centroids. Okay. So in transfer attributes, we're going to extract as well area. And right now, we go to the geometry spreadsheet. Nothing happens because area is not with caps. Area is with the small letter. And yeah, we already brought the attribute from the primitive to the points. All right. Cool. Okay. This is cool because later we can remap this area attribute. Okay. We can remap the area attribute. Also, make sure to compute the range because it automatically gets the minimum and the maximum of the input attribute. So area has a minimum and has a maximum. So compute the range and you're gonna get it. You're gonna get them automatically. And you want to set 0 as min and 1 as maximum. And we have our ramp. Okay. Okay, what's happening right here? We want to give me a second so I can double check something because I think that we don't need this primitive ramp. I think that we do need. Yeah, we don't need this attribute ramp. Sorry about this. I sometimes I get too excited. Yeah, if we also with a remap node, we rename the area to the p-scale attribute. This p-scale attribute is pretty important for scattering, for any operation that requires copy to points. Why is that? Because this p-scale attribute is storing a scale operation in the point that you are bringing. For example, here are a lot of points, right? So after the attribute remap, what's happening is that this area attribute is going to be remapped to the p-scale attribute. Okay, this area attribute is remapped to the p-scale attribute. Before we didn't have a p-scale attribute, we just had this area attribute. And after the remap, the p-scale attribute was created. And this p-scale attribute is gonna drive the scale of the it's gonna drive the scale of these copied lines. Okay, so you can just play around, like, again with the ramp, how big you want the tentacles to be. You can see, like, these lines are gonna be scaled according to the p-scale attribute over here. All right, that's what's going to happen. And now we have a gradient of tentacles, and we can check later that, of course, it's gonna work nice. Yeah, cool. And yeah, these sizes are pretty appealing. We can even have some even smaller tentacles over here. We can have this differentiation. Yeah, I am satisfied with this. Great. So that's how tentacles are done. But as I told you guys, later we're gonna check other ways of making tentacles. Also, to make these shapes to be more kind of organic, because if you notice in the final model, this is more organic, more kind of looks like flesh. What I done first here is that I splitted the group expand one. Remember, group expand one are these polygons. And what the split node that does is that in one output it gives us the polygons that are from this group, and in the other output are gonna give us it's gonna give us the other polygons, right? So it's splitting according to the group that we are introducing here. Okay. After splitting, we polyfill this, which caps the holes on the polygons. Remember that we had this kind of shells, but if we fill it, it's going to be completely sealed. And then I use remesh with this target size and with 10 iterations and with one value for smoothing. If I increase the smoothing, it's going to be a lot and it's going to reduce all the details. So I found this to be a cool balance. That's it for this flesh. Yeah, so we blasted this. Sorry, we split this, and then we split this again, but we are gonna split these two groups. We're splitting these two groups. So it all comes down to the groups that we created before. We're just splitting over here, like selecting which groups we want to. For example, here we split these groups, and then we split this group, and then it's a polybevel operation to have this with more detail. It's cool. Okay, and then yeah, another operation of splitting. I'm not gonna take too much time of this because it's more splitting and more poly extruding. Except this one, I think. Yeah, just to get this kind of to get this kind of inset. What I've done here is instead of using inset, I use thickness scale. That just because sometimes if we wanna use inset, it acts weirdly. So you wanna use sometimes the thickness scale. It's all because of the normals as well. So I split that, and I split that. I created a front group, and I named the front group as panels, and then I split the panels, right? So here it's split, and with a primitive wrangle, I set the alpha at 0.33. So this gives this kind of this transparent appearance, this transparency for these primitives. Okay, and the groups that are not these panels, I thicken them. So you have these thickened areas and these panels that are kind of transparent. Of course, we could have designed some interiors here, but maybe later, maybe in another tutorial. And also, these are some scattered details, okay, over here. These details, first of all, you want to model them, and it's kind of the same logics that we followed previously. We extrude, we transform, we symmetrize this unit, by the way, and we symmetrize in this direction. So it creates kind of a mirror of this geometry. Then polybevel, and then this kind of inset of this geometry, and then I rotated and scaled it. And so I think yeah, this is the same logic that we followed before. Like we fetch the area, we transform it. Sorry, we move it to the centroid. We transfer it to the centroid. We transfer the attribute area to the centroid, and then with ray, we don't need this normal, I think. Sometimes I get too excited with the normals, as I say, but collision primitives. Oh yes, we need collision primitives. Yeah. Okay, so we brought the normals here, and also we remapped the P scale attribute. Also, this attribute needed to be created as well, because check what happens if we do not have an up attribute. It kind of scatters them randomly, right? So this this is not very organized. So we need app attribute as this vector, because what this does is that we are creating an app attribute on this direction, on the C direction, right? On this vector. And this is what gets us to these models. These models, sorry. Great. It took kind of a longer time than I expected because I needed to explain some basics. So if you guys agree, I wanted to take a break because I need to take some water, maybe 5 minutes, and I'm gonna bring water and stretch my legs maybe. So please feel free to drop any questions in the chat, because next we're gonna have more complex operations, and I would like us to be on the same page. But as I told you guys, if you have any questions or anything, please let me know. I don't know why this. Yeah. You want to check other operations. Yeah. Know why this broke, but yeah, we're gonna check some other operations. So yeah, I'll be back in 5 minutes. Well, hi everyone. Hopefully you're back. And I want to show you guys, yeah, another way of make tentacles. Yeah, I got too excited with the tentacles too. But yeah, this is gonna be very worthy because because we're gonna also learn how to make a Houdini asset out of a tentacle. And what's an asset? An asset is like a stored network that you can use in different ways. Like for example, you can make it your own node. You can you can even export assets to other softwares such as Unreal Engine or well, there are different softwares that you can import assets. But those are pretty useful. In this specific case, we're gonna learn how to use them for to make our own nodes. For instance, um, uh, we're gonna follow a specific workflow to make a tentacle. Okay. So we need this. So what's gonna happen here is next. We'll make a line. We same way as before, and we pick the first point of the curve with the point running this Vex expression over points, resample the curve, resample it. Okay, that's cool. Also, super important. We want to have in this resample node, we want to have this curve view attribute. What this curve view attribute does? This curve view attribute gives a value to every point. What does that mean? That every point over here is going to have a value according to its position to the curve. For instance, the first point is going to have an attribute of 0, and the last point is going to have an attribute of 1. Okay, and of course every other point is going to have its own attribute, like its own value, whatever we want it to be. Okay, cool. Next, this value we're going to remap. We're going to remap. So this curve view attribute is going to have a width value. So a width value that we can modify. For instance, with this ramp, we can modify this value with this ramp to have a shape with different thicknesses. Okay. Okay. So we're gonna have to do just one simple line of coding. Well, not that simple. It's simple. It's simple. So first, what do we want to do? What does it do? We're gonna create another attribute wrangle. Now, for instance, we're gonna create a width attribute. Okay. Also, remember to finish every code with semicolon. I hope this is that's the right word for this symbol. But yeah, right now we are creating a width attribute, but this width attribute is all 0, right? Because we haven't done anything right now with the width attribute. Okay. Okay. So this width attribute is going to be equal to a ramp that we're going to create. How do we create a ramp? CH ramp. This is the code. Sorry, this is the expression that we need to create a ramp in PEX. Okay, we need this CH ramp line. Now, what is this ramp going to map? Because if we want a ramp, we want to map an attribute, right? We need to map the attribute called curve u. Okay, but before this, before using the curve u attribute, we need to name the ramp. This ramp is going to be named with okay. So we just need this to create the ramp. We need the ramp name with this, also these symbols over here, these symbols. We need a comma, and we need which value we are going to map. We are going to map the curve u attribute. Okay, that's pretty cool, because if we click on this button, creates a spare parameter. So it creates automatically the ramp that we are bringing over here. So we click here, and this is what creates the ramp. Okay. So right now we're free to play with the ramp. Like we can use any mapping here, any shape. And what's gonna happen is that it's not mapping anything. And why is not mapping? Oh, sorry. This isn't. Know what happened there? Yeah, I don't know what happened there honestly, but yeah, never mind. We have a width attribute. So you can see that if I start playing with the ramp, these values are going to be altered as well, and all according to the curve view mapping, right? We're mapping this 0 value to be 1 over here, and we can map this to be 0 again over. I mean, we can remap these values any way we want, and this width is going to become the width for this polywire node. For instance, we can use polywire. We can use polywire, and we can bring the width attribute. And how do we bring attributes? With the add symbol. Add width. Sorry, width. Great. We have this radius. This radius depending on the width attribute. This radius is going to be the same as the widths that we're writing here, right? So we can start playing with the ramp and have any shape. And also I suggest you guys to change the shape with to be spline, because it gives a more smooth profile. Okay, so you can play with the ramp any way you want. So the shape is also pretty cool. Yeah, also, there is something missing here. What's that? This ramp only maps values from 0 to 1 to 0 to 1, meaning we cannot have the minimum value over here. The minimum value of the ramp is always going to be 0, and the maximum value of the ramp is always going to be 1. But we also want to control it. Like, we want to control what's the minimum and what's the maximum of this ramp. Okay. So what we're gonna do is use another function, which is called fit. Okay. Like, imagine so we're precisely running the fit option, the fit function over this ramp. Okay. So we use parentheses around the ramp function. Okay. Yeah, it's giving us an error because we haven't finished the function. So what we want to do with fit is map from 0 to 1. I don't remember if I need, I need a comma. We're going to remap from 0 to 1. These are the origin values, because right now what's going to come out of this ramp is a value from 0 to 1. But so we're going to map values from 0 to 1 to another channels called, sorry, to other channels, 2 channels. So we have 2 channels. Yeah, 2 channels. So these are the origin values, and we're going to have 2 new channels to run. And one is going to be called mean width, and the other one is going to be called max. Sorry, I'm missing these symbols. Max width. Cool, and now it's running, but it's not giving us any polywire because we're missing the creation of the parameters. We click on this, and we have this new min width and max width new parameters, right? So I can set the max width to be, for example, 5. So we're gonna have a match thick structure over here. We have a mean thick of 1. Sorry, a mean width of 1, and it's gonna the width of this value. The width of this wire, this polywire, is going to be much thicker, right? So yeah, we want to explore this a lot. It's pretty useful. So what I've done here is exactly the same. We created a tentacle with its mean value and with this max value. It's exactly the same code. So basically, to check this again, we are creating a ramp. Sorry, we're creating an attribute called width that is depending on mapping the curve view value with a ramp called ramp width. We're creating this ramp over here, and then we fit the values that come out of the ramp from 0 to 1 to these new channels min width and max width. It's basically it. We are basically mapping the curve view values. And that's what gives us the tentacle. Okay. So So let's jump onto the next, onto this first pattern of tentacles. What's going to happen here? What's happening here? So we started with a line and also a grid. This grid is a 10 by 10, by the way. Oh, sorry, 100 by 100. And we use the scatter node to scatter 1,000 points over the grid. Okay. So these points are being scattered all over the grid. And you can also play with these values, okay? Like relax iterations. Relax iterations always tries to give us a more uniform scattering. It's too much. 100, maybe I use 100. A much uniform scattering, but we don't need that. We need this to be pretty random. This attribute I'm gonna show later, because first I want to show that well, I copied all the lines into the points, into the scatter points over here. So with copy to points, all the lines are being copied to the line. This ones. Also, I resample them. Are being resampled, and basically the same workflow that we followed before, right? We use this group expression to fetch the starting points. With instead of using mountain, here I just point jitter, but basically it achieves the same purpose. Like you can play with this, but it has less parameters. You can play with a scale, you can play with a sheet. It's up to you. But it gives us different. No, sorry, it gives us the same result. Then I smoothed it, so we have this kind of hairy, hairy looks, and we start with this sub. We use this loop to run this function over all the curves, to create these tentacles. So what's inside this subnetwork? Double click it, and it's exactly the same. This is exactly the same nodes that we were using before to create the tentacles. Remember, yeah, it's exactly the same workflow. Exactly the same workflow. We use polywire even to create the tentacle. It's exactly the same workflow that we were talking before. So we convert all this workflow over here. It's all converted in an asset. It's converted in a node that transforms a curve into a tentacle. Okay, so how do I come from this to one node? Simple. Just come to assets, come to new digital asset from selection. Well, first I'm gonna duplicate this, okay? So we can check the difference. First I'm gonna duplicate. So this is all the operation that is going to is being applied. This is all the operation that is being applied. So this operation is what we're going to transform into asset. Asset and new digital asset from selection. And this is how you how it allows you to name the asset. For example, I can name this asset to tentacle Tentacle, tentacle side. And also it allows you to select the sub menu. There are a lot of sub menus in Houdini, but I suggest you to keep the digital assets in the digital assets menu because it's gonna, I mean, sound you actually, but depends on what you need. And you wanna also save this asset into a place, into the same place that comes from default. If you wanna use this asset in different Houdini files, like it's gonna automatically load into your into any Houdini file that you're working on. So yeah, it helps you to do that. So yeah, when we are finished, we create, and after we hit create, it yeah, this doesn't. Yeah, this is somebody. So we created the tentacle asset. That's it. As simple as that. So if you wanna use this asset again, you can come to digital assets and here you have the tentacles node. It's as simple as that. Okay. I can delete this. So so what's happening here is that after after smoothed curves, I used a loop. I think that the loop needed here is for each primitive. I think. Let me recall this. Yeah, it's for each primitive. Actually, for each primitive node. Oh, that's cool. We don't need this node. So yeah, that's the workflow for creating these tentacles. What's missing is these attributes, because if you notice, we can also create some variations on the pattern, and we're gonna create variations the same way as we did with the tentacles before, meaning we can have some tentacles that are bigger than others, right? And how are we going to achieve it in this specific workflow? We're using a scatter, but I also want to bring attribute attribute paint. So this attribute paint node is pretty useful when you want to literally manually paint an attribute over a geometry, over points, I don't know, over polygons. Like you wanna use this node. And how do I use attribute paint? You just hit enter, and you have this new interface. So you have this kind of brush, but it's pretty small. You can see that red dot on my mouse. That's the brush, but the brush is pretty small. So if you wanna make the brush bigger, you just scroll the mouse up, and you can see the brush radius is coming higher right here, and I get a larger brush, and I can start painting. Like literally, you can just click. What is it? It's not. It's not. Oh, sorry. I don't know why it didn't paint, but right now you can see that it's paint. I'm not sure why it's not painting. Yeah. Maybe I have a bug over here. Because when I drop the pencil, when I drop the brush, it doesn't paint anymore. Never mind. So I can start painting over here. Paint, like paint some areas where you want the attribute to be higher, meaning that the red dots will have a higher value than the blue dots. Okay, that's important because this is creating, oops, sorry. This is creating a new attribute called mask. And you can see it here, a new attribute called mask. Okay. And you can see the attribute in better detail if you hover your mouse over the node and you click this info tab. Okay, just click it, and you can see that here are the attributes created. The attributes that are stored in the node that is over here, right? So you click mask, and you can see like this mask attribute is going to be shown outside this attribute paint. Okay, so that's what happened over here. I painted the mask like so. I just painted a mask, and then I blurred the mask. And maybe the difference is not shown radically. Maybe I need more iterations to blur. Nope. I never mind the attribute blur is not doing much over here. But never mind. Yeah. Remember that with after you create the attribute paint, you're gonna have the mask attribute, and when you start using the attribute blur, you're gonna have to write down here that you want to blur the mask attribute, okay? And then we do the same process that we did before. Remember, we mapped previously we mapped area to P scale. Now we map mask to P scale. In that way, we can have lines that are going to be higher than the other lines, right? So I am very curious why this is not smoothing. Because attribute blur is supposed to smooth transition, but it's not smoothing anything. And I'm not gonna check it right now. Maybe later I'm gonna update this, but let's ignore attribute blur. Yeah, we can already uncheck the mask attribute over here. And that's how you get this kind of pattern with larger tentacles in some areas. Okay, cool. We can expand on this concept pretty much deeper, because what if, for example, we use the torus node. I created a torus with these values, like
This is the internal radius, and this is the profile radius, okay? And you use a scale, rows, columns. I use the mountain node to to um, to give it a little to have a different shape. Basically, it's just a matter of randomizing a bit the shape. Then I use attribute noise. What attribute noise does? This node, and what this achieves, we are creating an attribute called mesh sizes, okay? And this attribute is gonna be useful for us for this remesh node. Why? Because if you notice, this remesh node has some denser areas than others, right? This kind of deformed donut has has some denser areas than others. Okay, we can achieve that with a remesh node, but first we need to create these sizes, like these density areas, and we're gonna create this with this node, with this name, with float, because we don't need them to be vectors, because vectors are used for colors, are used for movement, but we just need simple floats, simple numbers, okay? And we can even, with attribute noise, we can use different noise types, okay? So we're creating with a noise an attribute called mesh sizes, basically. That's the purpose of this node. And later we are also remapping the mesh sizes, okay? Because we want some because this noise is pretty low. Like you can see here, we can increase the amplitude, but it doesn't. I rather do it with the remap, because you can see here that mesh sizes are 0, some are 4, so it's pretty small, or pretty different. Right? So to kind of normalize it, we use attribute remap to have higher values as well. And this attribute, mesh sizes, the remap attribute, is gonna come as an input for the next parameter, for mesh size attribute. I use mesh sizes as an input, and also in an adaptive mode, because you can remesh it regularly, like so. Remesh, you can remesh it regularly, and you're gonna get this. You can also play with smoothing iterations. How many I use? Checking, for example, and you're gonna get this. But what this is gonna lack is a differentiation on the polygons. You're gonna get always kind of the same polygon. It's not gonna be the same, maybe 1 or 2 units of difference, very small difference, but it's gonna try to achieve like a regular length for all meshes, okay, with a uniform mode in each length. With the adaptive mode, we're giving it even a relative density according to a parameter, sorry, according to an attribute that we have created, which in this case is, of course, mesh sizes. Okay, so mesh sizes is useful for us to have denser areas, denser polygons, than others, right? So that is useful for that. Next, we used we have to use how do I put this? We're gonna place tentacles on this shape, okay? We're gonna place tentacles. So if we have tentacles all over the geometry, it's gonna come very crowded. So we have to reduce the amount of points that come out from this mesh. Kind of randomize the points that we are picking. So with group one, with the group node, we're gonna be in the point, and we're gonna run it over points, and then we're gonna use the keep by random chance option. Okay, so we use a seed and we use a percentage, and we're getting back a group of some group of points, right? A random group of points. Later, I use attribute rename. Why? Because not only I want the mesh sizes attribute to affect the sizes of the polygons, but I also want mesh sizes to affect the scale of the tentacles, meaning that at the end, what we're gonna get is some larger tentacles in areas where polygons are less dense. In smaller areas, in denser areas, we're gonna get smaller tentacles. Okay. So well, the rest is kind of history, because it's kind of the same story, because you have to copy two points. You have to copy two points. You have to resample curve, get the curve base. Sorry, get the starting point, expanding the starting point, jittering the geometry, but not the base points. The base points you do not jitter. You keep them in the same place. Later you smooth it, and then you use the loop for each primitive, right? Over here. So that's what's needed. And yeah, that's what's needed. Next, next, I want to introduce you guys to BDBs. BDBs are pretty useful tools for these purposes. I mean, you kind of like this idea, but what BDBs does, what BDBs do, is kind of I don't know if you guys have used Dendro in Grasshopper, but it creates not polygons but volumes out of the geometry. So it kind of voxelizes the geometry. You can see here that there are many voxels. Voxelizes the geometry. And you can use you can modify the voxel size with this parameter. Then you combined. Then you can combine better the geometry. Of course, you can use Boolean operations over here. Of course, you can use them here. You can Boolean union them, but BDB combined, with BDBs, you can later use BDB smooth and have this more kind of organic shape on the polygon, right? and then you, but of course, by the way, BDBs are only used in Houdini, so you can't export them to other softwares. So, of course, BDBs are pretty handy for these operations, for smoothing, but later on, you're going to have to anyways convert them to polygons. So you can convert BDBs to polygons with convert BDB, and you convert to polygons, okay? So, to explain this better, I just convert these polygons to a BDB with these voxel sizes. Then you have to BDB combine these all geometries, because these BDBs are all different, and you have to combine them. You can combine them with this operation with add. Then you later on smooth it, smooth the geometry, smooth the volumes, sorry, and then you convert them to polygons, and you have this geometry. At the end, I like to use poly reduce because check how the wireframe is after poly reduce and how it is before poly reduce. So as we're working with voxels, voxels are pretty dense. So with poly reduce, this density is going to become much lower, right? And the details on the geometry are not very different. Like you can see here is the previous poly reduced and after this poly reduced. Basically, there is almost, I mean, I can see any difference. But if you go with a smaller value, I mean, I kept just 45% of the geometry. But if you, for example, want to keep 10% of the geometry, you're going to start losing detail, right? So you want to find that balance between detail and amount of polygons. So maybe 45% was okay. I'd say this was okay. Cool. And you want to use poly reduce because if you want to export this geometry to other softwares such as Arnold, or such as Maya, you want to have as low polygons as possible because because the file is going to weight a lot, and it's going to be much harder to work with, and it's going to take longer to render as well. You can, we're going to check in Arnold some features to smooth this as well, because if you zoom in very close, you can see the polygons, right? Even some normals are kind of no, normals are okay, I guess, but maybe we can normals are okay. So yeah, this is how you create this creature. Cool. Okay, this is also pretty cool, a pretty cool exercise. It's kind of easier, okay? It's kind of light. Even though we have a lot of lines of code over here, it is pretty easy. Why? I wanted to tell you guys that ChatGPT helps a lot with writing codes. For example, I told ChatGPT, you can even use DeepSeek, okay? DeepSeek is also very useful. I've done some cool animations with DeepSeek. It's something to check. But the downside of DeepSeek is that you don't sometimes it tells that the server is busy, so I didn't want to use DeepSeek right now because of that, because maybe the server is going to be busy right now. No one knows, but never mind. I told ChatGPT these instructions. I have a 100 by 100 grid in Houdini, and I want to get the best code that helps me group primitives in a way that resembles the Manhattan noises. This code should have axis-aligned shapes with fractal structure, fractal-like structures, and also I want to have random and scale controls. So, ChatGPT gave me this code, which I used over here. I literally copy pasted, and then I can just create these parameters over here. And then it's gonna group it's gonna group the it's gonna group the geometries that I told it to group. Sorry, that that achieve the shape of the noise that ChatGPT used for this code with the instruction I gave ChatGPT. So we have different controls over here. For example, how many layers we have, complexity. We can have a different scale as well with the noise. I can also, maybe I can increase the resolution of the grid. So yeah, we do even have a threshold parameter. We have a seed value as well. So this is pretty interesting. Maybe this isn't exactly, but ChatGPT also helped with the creation of this. How does that happen? In the following question that not question, I just give ChatGPT an instruction. I told ChatGPT that I want a similar code but with Chebyshev noise. It wrote the code, of course, here. I just copy pasted over here, and it returned a group called Chebyshev group. In the base group, we can, of course, pick the group that we want. So I brought a group node here just to visualize this. What's grouping? What the code from ChatGPT returned, right? Also, I use group from attribute boundary to group, of course, the boundaries from this group. Then edge group to curve. It's the same that we have used before. And with a polyfill node, we can create single polygons for this curve. And this is what I got from the code from ChatGPT. So check also that we can also play with these parameters. For example, we had this, but if I start playing with the parameters, I can get another configuration, right? So this is pretty useful, even different scales. I mean, the options are very, very varied over here. You even have a threshold parameter. It's up to you guys how you want to explore this. But yeah, this is the result from the code, and I can start playing this with this even further. For example, I can create kind of a city out of these shapes. And how does that happen? So so if you see after polyfill, something interesting about Houdini is that after polyfill, it returns not only the single polygons, but the curve that is surrounding the polygons. So if we want to delete this white curve, the thing that you have to do is output the group patch. You have to output the group patch. Oh, by the way, make sure as well that the patches are on the right direction, because if you don't have the reverse patch option, it's gonna come downwards, but we want them to face upwards. So they extrude upwards. So we output the group patch, and with the blast node, we delete the groups that are not from the group patch. Polyfill with the group patch outputs only the polygons that it's created. So that's important. Okay, next. Next. Here I created two attributes, okay? Here there are two attributes. Yeah, so take a look at this. Take a look at this. Somehow creating something random. Yeah, this is interesting. Yeah, never mind. I am using here the connectivity node. What this achieves is creating an attribute called class. Why do we need this attribute class? Because we want to extrude the we want to extrude them differently, right? We want to extrude the buildings different. Okay, we want to extrude them different. So we want to have this class attribute. So we have different numbers for each primitive. Some numbers are repeated. For example, here is 21, and here is 21. But that's cool, because what this node does is that it creates the attribute depending on whether the primitive or the geometry is separated, or if it has kind of a contact, or yeah, depending on that. For example, yeah, I can't see exactly where, but maybe two curves are just touching, but it's creating them together. And I'm gonna check that later. But yeah, it doesn't. So this class attribute is gonna kind of give us an ID, like an identification number that we wanna have for these expressions. So, yeah, this first introduction to attribute Bobs is pretty useful. What's an attribute bob? Attribute bobs are pretty useful to do operations over not geometries but attributes, and also it helps us simplify some VEX coding, because some operations are not directly used in Houdini, or there aren't any nodes in Houdini for those specific operations, so you have to do it in VEX. But sometimes you can avoid using VEX using these attribute bobs. Okay, cool. And this attribute bobs is also another environment, like another, yeah, you have to double click it to access it. Okay. For example, I have created an attribute bob over here. And what does this attribute bob does? This creates one attribute called extrude, well, rand. It meaning extrude randomly. I just simplified it. But we have this extrude rand to have, it's the same logic than when masking. Remember, when masking, the red ones were the higher and the blue ones were the lower. So it creates like a random random extrusion value for every primitive, and that's cool because we can use in poly extrude, we can use the extrude ramp as distance scale, this attribute extrude ramp as distance scale, and start extruding the buildings, right? So that's pretty neat. Okay, but how do we create this extrude ramp attribute? So there is a simple step. This we're gonna check after. Yeah. These ones are the nodes that create this attribute. Okay. These ones are the nodes that create this attribute. So first, we use this node. It's the same way that you call nodes here the same way that you called it outside this node. It's called import. Remember that the class attribute is created in the primitive context. Okay, so we have to import a primitive attribute. A primitive attribute. Okay. Also remember that class attribute is an integer. Okay, class attribute is an integer. So instead of vector 3, you click integer. And in the input is also very important. You have to click on first input, because on the first input of the attribute bob is where we are connecting where we are connecting the geometry. Okay, so we import the attribute, but we also want to name which attribute we want to import, which is going to be, of course, class. And this is how you import a specific attribute from outside the bob context into the bob context. Okay. Cool. Also, it is important for us. It is very important for us to convert. Sorry, I think my cat is in a mess. Yeah, so we want to import the class attribute, okay? But we also want to transform the class attribute to float. because remember that we had the class attribute as integers. After transforming them to floats, because of using the float attribute, we transform this. Yeah, we're getting the extrude random attribute is going to be a float, right? It's not going to be integers. Great. Yeah, the same happens with extrude sort. Yeah, normal. Also, we are using random to randomize the values from class. So yeah, also it's one D float input and one D float output. Okay, so we are randomizing the class attribute, and then to export the randomized version, we use this node called bind export. Bind export. Okay. So you bind export is the result from the random, and you can name this new attribute however you want. I named it extrude random. You can place any name actually. And this is how you create a new attribute from the class number, from the class attribute, sorry. And then we are polyextruding, as I told you guys, like come to local control, distance scale, and you extrude randomly these floors, okay? You can also use this other attribute that I created, scale, no, sort. Yeah, you can see that it's kind of sorted in this direction, like with a gradient from here to there. But this is created in a different way. How? The class values, the class attributes, sorry, we want to fit them from 0 to 1. Okay. What does fit mean? It's the same as remapping. You have a class. You have a class attribute on every primitive, right? You have a class value on every primitive. Yeah, kind of the same. Kind of the same. So what you want to do is that the number of primitives, this comes by default, by the way, is geometry bob global. So the minimum value for the fit is 0, and the maximum value for fitting is going to be the number of primitives, which, as I told you, is around the number of class. So we're remapping the class attributes from 0 to the number of primitives. We're remapping from 0 to 605 to 0 to 1. So we are feeding those values small. And it is sorted because we haven't done any random operation. And by default, these primitives already come sorted. So class is also kind of sorted. The class attribute is also kind of sorted. So yeah, that's the logic behind it. So you can see here they are kind of sorted. I think it's sorted according to the center. But yeah, that's the logic of this. Here are the primitives. Yeah. We haven't done any random operation, and they are already sorted. So we are using these numbers from class to create a new attribute called extrude sort. But yeah, extrude random looks more natural, right? Cool. Yeah, I got a little crazy with this because um I don't know how I was working this. Do you have anything? Yeah. Yeah. So what I wanted to do here as well is to create like different floors, different shapes of buildings, and it can be achieved if you first, I think this attribute, I'm going to talk about it later, but first you have to create the floors step by step. And and then do a loop operation to copy every floor differently. So to achieve this, what's needed to happen? We have to create an attribute called floors. We have to create an attribute called floors to determine how many floors each building is going to have. Okay, so each building is going to have different floors thanks to this parameter. Okay, and it's basically fitting, like a fitting operation. And also you want to transform a float to integer. I mean, we're transforming this attribute extrude randomly from 0 to 1 to 3 to 19 and transform it into an integer. And then we're using this is called a for each piece connected piece loop. So this is what returns. So we're gonna promote the attribute floors from primitive to detail, because primitive is can be a polygon, but this detail piece, this detail class, sorry, means a whole block. Yeah, it's like in AutoCAD or when in Rhino you have a block made out of different polygons. So primitive is usually referring to it. Primitive usually refers to polygons, but details refers to the whole block. And then we copy the floors. Yeah, here. I use this piece of code, which fetches the attribute from this node, okay? The values from this node. So yeah. Also, please remember that you wanna use the first match This is a mode that works better for this purpose. So yeah, and this code fetches the floors attribute from this node. Okay, detail. We're gonna dive deeper into these codes later, but basically it accesses the detail in the detail class, then goes to the node, then goes to the attribute, and this 0 is to I think it's because of the type of the attribute, but usually I use 0. I'm not a Bex Pro yet, so yeah, and that's what returns random number of floors. The minimum is gonna be 3 because we set the minimum to 3 here. And I can use 2 as well. Some of them are gonna be smaller, but maybe some other blocks I can find later. Later, you can group the floors, and then you can group the floors, and then by normal. By the way, I use normal here, and then you can create a group using the base group as floors. But as I told you, you can use this exclamation mark and get every group but the floors here, right? Yeah, also, I have a spread angle over here, so some of them that are very inclined are not being selected for Windows. So yeah, I am using here the base, the all but floors Windows, and then as Windows, sorry, and then keep by random chance. And this allows us to get randomly primitives, but not floors. We're not getting any floor over here. And then you can poly extrude this, and then I use a split to split. Remember that we can get the front group from this parameter, and then I split this, and I got the windows. Sorry, I got the extrude from one side, and I set the alpha attribute. I color it in blue, but yeah, you can color with this node. You can just click here and select a color, whatever color you want, and this is how you get a city. And these are the roads over here. I just blasted the Chevisep group that ChatGPT created. Okay. Yeah. Also, to go just a little bit faster. Yeah. So you can. ChatGPT also helped me create this mask. Okay. How does ChatGPT achieve it? There is a new question that I asked it, and it's called. I told ChatGPT to get a VEX code that helped me group primitives in a way that resembles a chart Giger art, and to ask me 3 questions before writing the code. And yeah, because this is very vague, right? I mean, to define it better, I told ChatGPT to ask me 3 questions. And yeah, it asked me the questions, and I answered them, and returned me this this code, sorry, over here. Also, yeah. Remember that I told ChatGPT to group primitives, okay? So I can use primitive wrangle, use this code, copy it, paste it, click here. Oops, no, it doesn't have any. And I can get the group here. And it groups me this. Okay, but this is very very boring, right? It's like reminds of this Rorsch test. Pretty weird, pretty abstract, let's say. So I told ChatGPT to try an attribute approach. And this is very important. Why? Something that I haven't mentioned, guys, but it's very important to notice is that groups are stored as 0 or 1, right? Meaning it's a Boolean. It's like you are from this group or you aren't, right? But what's an attribute? An attribute that can have these varied shapes. Like an attribute can go from, it's a float number, can go from 0 to 0. I mean, it's pretty broad. Like you can get different kinds of values. You can get these ranges, these gradients over here. Okay. Also, I taught ChatGPT to create some parameters like scale and resolution, and it helped me create these parameters, which are pretty useful. For example, I can use how much. I can use this parameter to regulate how much detail I want it to have, to the general scale. I mean, it's pretty useful. Right? You can see here as well different shapes. Yeah, and then I promoted this to from primitive to point attributes. Notice that primitive storing attributes in primitive means to color the whole polygon with one color, of course. But storing the attribute in point is more diffuse, because as this primitive has 4 corners, each 4 corner can have a different color. But if we store we store the attribute in primitive, all the 4 corners are going to have just one color. Okay. Later, I've done this. So how it happens? You can create a sphere, and you will project create a projections for a UV projection on the sphere. I click this, by the way, show UV texture when UV is pressed. So this sphere now has a UV map. So the projection is a polar projection, okay, for this specific sphere. Also, I created a projection in the grid. So those two geometries have a UV map, okay? Later, with the attribute transfer by UV, you can project the attribute called Giger mask. You can project the Giger mask attribute onto the sphere. So it's projected over here. And now this sphere has this projection, right? So then with soft peak, I created a distance attribute called Giger mask and apply a roll off and also a distance to the extrusion. Also, as I told you, remember to use this attribute distance metric. Okay, your mask, surf radius, and that's it. And that's it. You can create. We're gonna later use this as a shader. I'm gonna show you guys how to create a shader from these maps, because you can also use the color node to create an attribute to create color from the attribute called Giger mask. And I use this, for example, Inferno, I think, ramp. It's Inferno ramp. I can make more black colors or enhance purple colors. It's up to you guys how you want to enhance it. I smooth it a bit, and this is going to be our new texture. And yeah, I'm going to show you guys later how to create masks. But first, because time is getting short, let's jump into creating some other geometries before jumping into Arnold, because this pattern we're gonna create a shader in Arnold, so we have to export it first. But to finish with Houdini, I'm gonna show you guys how to create these geometries. Yeah, it's a pretty long road actually. It's a pretty long road. So I created a sphere, okay? And this sphere, let me double check this. Yeah. So from this sphere, I want to get two things. First is this interior kind of shape and the shell. So what's gonna happen first? I wanna give it a more extruded in this direction. I created the horizontally, but then we can rotate it, so it's not much of a deal. Then I use the mountain noise, the attribute mountain noise. Oh yeah, hi Walter. Yeah, there is a link. I'm gonna share it here again. Here the webinar. Yeah, and then we created a mountain and remeshed it. This remeshing is pretty important to get more detail on the geometry. Yeah, this is also another attribute Bob. So what's happening here? What's happening here? Okay. There is a way I mean, you can use, of course, mountain to apply some kind of noises on your geometry, but to have a more personalized noise, you're gonna have to go to attribute Bob, to attribute Bobs. You don't have to go to attribute Bobs, okay? And in attribute Bobs, you can bring, for example, unified noise, and you can connect the points to position, and then you can displace along normal. You can displace these points along this. No, yeah, along these normals, and the amount is gonna come out of this noise. All right, and the displaced points are going as an output over here. So this is a different noise, right? So you can even change the shape of the noise to alligator and this creates a different kind of shaping. And you can create another kind of noises over here. Like you have different different kind of noises to create here. Okay. And yeah, I mean, you can modify the parameters here, the frequency, the noise. Like if you wanted to make it smaller or bigger, like so. It's up to you. But the workflow specifically for this kind of noise, then I delta smashed it and then I sharpened it, is the following. You bring the noise, preferably it's an AA noise, anti-aliased noise, and you fit this noise, because this noise comes from, oh, you of course you can modify the frequency, the amplitude, how raw you want it to be. There are a lot of parameters to play here. So this anti-aliased noise comes from minus 0.5 to 0.5, and you want to modify it to 0 to 1. Also, this modulo here is what creates these peaks, because without it, what's going to happen is this. All right, so we're getting this this kind of lumps over here. It's cool as well, but module helps us create this kind of blades or ramps in the middle of noise. There is a mathematical explanation for it, but it's gonna take a while. So kind of rounds the numbers in the input that you place here. Also, I used a ramp to remap the noise. I used a ramp to remap the noise before using it as a displacement, as the amount for displacement. So yeah, this ramp is what's used for it, like remapping the noise. Then, as I told you guys, delta smoosh it and mesh sharp. And the same process goes actually for this one, for the interior, because remember we have the shell. This is the shell, and we have the interior of the egg. Okay, of the egg. Also, this node is pretty important for us. It's called mask by feature. Okay, we're gonna create a mask. Okay, what does this mask achieve? And we create a mask along one direction. What? Yeah, this direction, the X direction. And I'm gonna bring another mask by feature. Mask along this direction, and we can increase or decrease the values of it. But you notice that there is a mask being created according which polygons face this normal. Okay. Specifically, but for this mask, I created 1,000 blurring iterations and a very high angle. So it has this blurred effect. Okay, then I applied the same logic of the noise that I told you guys previously, but something very important is that I imported the mask attribute from the output one. The output one is, of course, the sphere masked. I import it, and then I remapped the mask with a ramp. And then this remapped value of the mask, I multiplied it with the noise. And this noise, of course, has different parameters, right? You can check here. And you multiply the noise with the ramp, and that's it. Then delta mush it, then sharpen it, and that's a whole story. I poly reduced it, by the way, because it doesn't need too much detail. And that's it for this part. Okay. So here's a longer part actually. Linear taper. I used linear taper to give this egg a more egg-like shape, not too flattened. So linear taper helps a lot with that. I rotate it, of course, and yeah, I separate it, and I remesh this one. Yeah, this is a very important workflow as well. I wanted to not to have the whole shell, but just this more convex areas on the shape, and I wanted to delete these concavities because it helps us like create kind of this armor to the egg, and then we can see better how this kind of goo comes down to hold the mesh. Helps better to understand it. So the workflow is the following. You cluster the points from the mesh according to what? According to the convexity attribute. What's clustering, by the way? Clustering is also creating an attribute, okay? But it's more like it's more like the class attribute, like it's integer, and you kind of recognize what's the difference, right? Like this is group 0 and this is group 1, okay? Also, and here you introduce convexity as a control attribute, and also you can choose how many clusters you want. I picked 2, but you can have like 4 clusters. Like it's totally up to you how you wanna handle this. But I created just 2 clusters, okay? Then I promoted the attribute cluster from point because cluster points is of course stored in points. So promoting it to add to primitive, sorry, allows you to have these more defined shapes. Because if we don't promote it, what's gonna happen? Sorry, what's gonna happen is this. Yeah, it's kind of it's getting us double lines. So we don't want that. We want the attribute to be promoted to primitive. And average is cool. It's cool. Sometimes you can use another, but average is cool. Then I smooth it these boundaries, because with edge smooth you can smooth any group of curves, and then you can also select how many iterations for smoothing you want, how strong you want the smoothing to be. And then I grouped and there is a way to call groups by attribute. So if you use the at symbol and you use the attribute, because remember that cluster is an attribute, you use at cluster and you say equals 0, you're gonna get in this group for every primitive that has the at cluster attribute equal to 0. Okay. So in group 4 are going to be all the primitives that have the cluster attribute equal to 0. Cool. Then I blasted it. Then you can use you can of course use here the poly extrude node. You can poly extrude this. Okay. But yeah, this poly extrude node is not so stable sometimes. Like you can change to point normal, but it even returns this kind of weird. There are some weird areas. For example, here there are weird peaks. Thicken helped me sell this. It's very useful for that actually. So I suggest you guys to use thicken when you want, but unfortunately, thicken does not have as many options as poly extrude. So I just wanted to thicken this, and so it's not just a empty shell, but it has like this thickness, so it helps. I don't need poly extrude for that. And the same process that we used before, right? PDB from polygons. This PDB reshape SDF. What helps us to do, I'm wondering if we need this at all. No, maybe we ignore this because I don't think we need it. Now we can smooth the. Let me check what exactly this accomplishes. Yeah, with PDB reshape SDF, we can use close to kinda enhance some areas. It helps a lot for that. Because without this closed, yeah, we can have like, as its name says, we can close some areas over here. It helps a lot as well to fuse some BDBs. Helps a lot with that. And then smooth. Then we convert the BDB to polygons. Same process as we did before. And then we poly reduce the polygons. Then symmetrize. And this is what we get. We delete the small parts. This node, delete the small parts, helps us to delete the geometries that are smaller than this threshold. Right now it's 0.05, but if I want to increase this, it's gonna delete a much more geometry, right? So in 0.05 is cool. So then I use color it, and this is what we get for this shell. Yeah, for the egg, there is not much story. The egg is the same egg, so there is not much creation on that. What's important next? Okay, we're getting a group. I didn't mention it yet, but you can also create group from boundaries. So these are the groups in these bounding regions. Okay, we're grouping this primitive in these bounding regions, and we blast the base. Yeah, we blast the group 5 that we grouped with this boundary, and then we create a normal. Why do we create a normal? To polyextrude this in the y negative direction. So if you see, there are normals for these primitives to extrude them in the negative y direction. So again, you choose point normal, and then you choose the existing normals, right? Also, some final modification that I made is that I output the group extrude from, and then moved it a little, so it has more like a base appealing. Yeah, it's more like base, not that pointy. Then I subdivide it. Yeah. Then we're gonna jump into some simulations right now. And for example, for this specific kind of simulation, because what it's gonna return at is this kind of goo. So for this specific kind of simulation, we need something. Oh, and what's the simulation about, by the way? It's actually very known. Diffusion, reaction diffusion. It's actually very known. It's actually very known. The logic of it is to subtract and enhance. And this subtraction and enhancing, what achieves is these patterns. Yeah, it's also a chemical. It's when two substances start to merge, they start to form these patterns. But yeah, I don't seem to find the right image for this. But never mind. We're gonna jump to it. Yep. Okay. So we want to convert all this geometry in a fog, and we're creating a hub with BDB from polygons, and we check this fog BDB, and so it has this density attribute. This density attribute is important to play with the solver and how it compares the differences through time. Okay. So we need this density attribute, in other words. Also, this volume bob operator, what does is normalizes all the voxels to 1. So every voxel here has a different value. Like the denser voxels will have a higher value than the less dense voxels. So with this volume bob, we normalize that. Then we convert the BDB to volume. It's still a volume, but it's not a fog anymore. And we jump into the solver. What does the solver achieve? So as I mentioned, you guys, you have the input in the solver. So this is the solver. I jump into the solver. This is the input of the volume. And what we do is yeah, we're gonna check this later, but right now this is what we get from the solver, right? Then we blur the volume a little. We're blurring it with these parameters and with this number of passes. So how many blurring iterations you're gonna have? And this does the same too. We blur the iterations this amount. So we have two volumes. One that is blurred one time and another one that is blurred 4 times, okay? Check this one here. This one on the right is more blurred. And then we want to subtract one to another. We're subtracting the from the one that is not so blurred, we subtract the most blurred one, and we get this volume. Okay, and then we can multiply these values that are getting after the subtraction. Okay, and this here, the final this final node. Oh, by the way, we multiply the result over here. We multiply it by 4, so it's more enhanced. Okay. And with these nodes, we're also saying that we do not want volumes smaller than 0.1. Yeah. If it's smaller than 0.1, then clamp it. No, sorry, I messed some information. So what this achieves, if it's smaller than 0.1, it's gonna be clamped to 0. Yeah, and we do want every value to be between 1 and 0. And that's it. And that's what this operation does. So if we start running the simulation, as a final step, we have to convert the BDB, from FOG to SDF. Okay. And I also tweaked some of this FOG ISO value to make it more noticeable. So if I start running the simulation, what I am gonna get is this. Okay. This kind of simulation. That's cool. But also, I try to make it a little bit more complex by adding a unified noise to in that last node that I was showing you. So I multiplied the unified noise with I just multiplied it, by the way. I didn't do anything else. I multiplied the unified noise to the before outputting, before feeding it, before outputting it, to the as a volume. I multiplied it with a noise, as I showed you before as well. So this simulation is kind of different because it also is constantly be receiving the input from that noise. So it does not get this. Remember, we had this very uniform pattern before. We had this very uniform pattern, and then we have this with the noise. Thanks to the noise, we have this kind of gooey appearance because the simulation is going to be output constantly interacting with the noise. Okay. So yeah, also I use this stash node because when I stash these inputs, I usually use these stash nodes when I am working with simulations. It makes the Houdini file a bit heavier, but it helps you to avoid this time of running the simulation every time you have to open the file. So yeah, that's it. And later on, I merged this final geometry with this shape. I merged them and combined the volumes, and then converted the VDB to polygons, and then symmetrize it, and that's it. And that's how you get this GUI shape. Okay. Cool. Yeah. I'm gonna run a bit faster on this creature because I think it's a bit of the same logics that we have done before. So we have a circle, we have a boundary, we have oh yeah, I think this one is a bit different. Yeah, let's go on. So we have a circle, and we extracted just a curve of the circle. We do not want the circle itself, but the curve around the circle. So I wanted to copy this circle on the on this line that has these points, resampled line. So I had to create an attribute. This attribute is called pscale. And this pscale attribute, you can check that it's has different colors because I activated the visualizer for pscale. It responds to this ramp. And how does it happen? So we want to create this. We want to create this new pscale attribute according to the point numbers. Okay, because each attribute, sorry, each pscale attribute is going to be run over points. Okay. So we want to have, for example, we want to have yeah, for example, if I connect it with the ramp directly, the highest number is going to have the highest attribute, of course, and the lowest is going to have the lowest. So we're dividing here the point number, meaning we're dividing 0 to the number of points. So we're dividing 0 to 20. So it gets us 0, of course. If I divide 1 to 20, we're going to get like, I don't know, 0.04. Okay. But if we divide 20 by 20, we get 1. Meaning we're going to get values from 0 to 1 from here to there. From number 0 to number 20. Okay. So that's why we are dividing the point number to number of points. Also, we are converting these integers. We're converting them to floats because we want to get floats here in pscale. We do not want to get just integers. Also, at the end, I remapped all the numbers that I got here, 0, 1. From 0 to 1, I remapped them with a ramp. So I can use this ramp to drive the pscale of these curves. Remember that copy to points, we use pscale to scale the curves. So that's what we're doing here. We're creating the pscale attribute to these points of this line. to copy these circles over the line, okay? So we use a skin to create some kind of loft. Then we fuse, yeah, we have to fuse these points because unfortunately skin does not close the seam. It always returns kind of a seam. So when you get, for example, if I want to polyfill this, it's not going to help me. It's going to do something weird. Just because if I bring group boundary, just because it doesn't close the seam. With fuse, we close the seam, okay? And we can finally polyfill this geometry. And then we remesh it to get this base shape. Oh, then I wanted to create a group, a random group here. So later we can use this node, group find path. So it creates it. So what this group wants to do is to try to connect every island. So each of these polygons is kind of an island, and it's gonna try to connect them all. Sometimes it does not succeed, but it doesn't matter actually. Doesn't matter for this purpose. So I extruded this shape. It's extruded. It's extruded the group find path. It's extruded. Then I moved the group extrude from. I moved them back to have to get a better shape. Then I use poly bevel, but just on the extrude front group. Poly beveled it, so it has this kind of shell. It's not so rough. Then a bit of smooth as well, but this is smooth. Yeah, it's just 4.3. It's a bit of a smooth. Then a remesh, and this remesh is also very important because I use a lot of iterations over here, like 10 iterations. Then symmetrize to get a symmetric creature. And then here starts the fun, because I grouped all the polygons that face in this direction with keep binormals. It's all the polygons in these directions are going to be grouped, and I blasted them. Also, I deleted the smaller parts, and with point wrangle, yeah, with point wrangle, yeah, that's also very important in simulations. In simulations, also something very important is the velocity. What's the velocity? Is a vector. It's nothing else than a vector. It's when you push something and that object is in that specific time moving a certain velocity. So we are setting the velocity to be -1 in the x-axis. So it's gonna tend, these points are gonna tend to move in to the left over here. So the pop network, what we're doing here, what we're doing in the pop network is of course a simulation of points, okay? Also, we're creating this static object, okay? Well, maybe let me remember how many nodes come here. These nodes are already coming by default, so nothing much to check on this. And these nodes are coming here by default. So the only node that we do not have, well, there are actually two nodes that we do not have, is a static object. I wanted to create also a collider, which of course is going to be this shape. This shape is going to be a collider, so the points are not are gonna collide with this object. So yeah, I brought it here. You can just click on this and look for the collider. And then after the pop solver, you want to introduce the forces that you're going to apply it. So for example, I introduced a wind force with a velocity as well of -1 and with this force. And also I play a little bit around with these frequency values to have this kind of simulation. The simulation is very, very cool because we can trail this simulation, okay? And we have, using the trail node, you can set how many frames it's gonna count, and it's gonna connect them as polygons. And also, please remember to uncheck close rows because it's gonna otherwise create a closed polygon. So yeah, it's important. These geometries are important for them. Sorry, these settings are important for them. So we're getting this kind of shape. Cool. So after that, maybe you can let it run a bit more if you want. You can make it. You can run it a bit more. It's on you. Up to you. So then you wanna have to smooth these curves, and then I also deleted some of them because I felt that it was too crowded. I deleted them, some of them just 15%, and then I stashed. Remember that stashing is helpful for saving this data, right? So we don't have to run the simulation all over again. Also, deleting small parts is very important, and I resampled them to have a more I resample them uh, to have less points, and then I fuse them. And when you fuse sometimes these curves, you kind of get these patterns, these kind of intersections over here that help a lot with a um, with a final geometry. Also, you can modify the snap distance over here. So right now it's 0.08, but you can increase the number, you're gonna get a completely different shape, or you can decrease the number and also. But yeah, it's up to you. You can just play around with this value, and also you resample them to create a curve U value. Because again, uh, because again, we want to create a curve at some tentacles, right? We want to create some tentacles. So also I made a bit of an exploration here because I do not want it only to be like a kind of a tentacle idea, but also I wanted to the points that are lower in the y axis to be thicker than the ones that are in the top. That's why this pipe, this tentacle, is even thicker than this one in the top. So check what happens if I unselect this, like all is the same and it doesn't show any difference. But when I activate these nodes, it shows a difference because I done some tricks over here. First of all, uh, I moved this I moved the curves to the center, and I also scale them. Scale them. So they don't, so they aren't bigger than one. Also, I justified to the minimum of y because I didn't want to have negative values. That's also a complication that I didn't want to have. So to have in the y position y values that are positive, you wanna you wanna um, you wanna have all the points above the plane, the ground. So I created a new attribute. This attribute is called y pos, and it's equal to the position of the points in y. So when you have a vector or a point in Houdini, and you want to get only one variable of that vector or point, you just call the point with @p, and you use point, and then the vector that you, sorry, the axis or the value that you want to get. There are x, y, and z, right? So you want to get y. And then I matched it back to its original size, because I only did this operation to get values from 0 to 1 in the space. And then I matched it back, connecting the points that already store the y position, normalized y position values. And I matched the size again to its original size. So later, I mapped again y position, the attribute y pos and the curve u value with this ramp, by the way. This is the ramp used for mapping, and then I use this curve to shape the tentacles. And basically, I did the same code as before, but instead of just using width, I created a new attribute called multiplier mult, and I multiplied the curve view with y position. So it does not only follow the y position, but also the position on the curve. So that's why some of them here are thicker, and some of the so some of them are thicker and some of them are thinner. I multiply these values, and instead of mapping the curve view value, curve view attribute, I map the multiplier. So then I symmetrize, because symmetry is always cool. And yeah, the same story. BDB, V-shape, smooth, and delete the small parts, and yeah, that's it. That's the story of these tentacles. Great, so we're gonna check a couple more details on this creature. Loads. Yeah. Gonna run a bit because it's already getting late. So yeah, it's the same logic that we followed before. I remeshed it to have more detail on the geometry. Meshed it. I measured the curvature on it, cluster the points. I cluster, but this time I cluster in 4 clusters instead of just 1. I symmetrized it because sometimes remesh doesn't give the same symmetry. Sometimes remesh doesn't give symmetric remeshing. Also, I promoted the cluster attribute from point to primitive. Here is promoted, and here it is. Yeah, already smoothed as we did before. There is no much mystery in that. So we chose here the cluster number 0 and the cluster number 1, and I poly extruded the cluster number 0 just a bit, and the cluster number 1 a bit less. So we have this kind of shell or armor for the creature, right? Have normals created, and that's it. Also, here's also some important workflow to create this kind of alligator patterns. It's pretty interesting. I'm gonna show you. So I've got the two meshes here. Made a mesh sharpen operation here to get more of these defined geometries. Remeshed it a bit and smoothed it just a bit. Measure the curvature. Also, yeah. Also here, let me check. And so here what we got. Yeah, notice that here we have denser polygons as we approach the head, and then no, sorry, the opposite. We have denser polygons as we go away from the head, but we have bigger polygons on the head, right? So how is this achieved? Remember that with remesh we had this option to use a mask for remeshing, right? So first of all, I wanted to remap convexity, the convexity value that I got from the measure curvature node. So we remapped it. And we also got this this way of how it's called, this way of remapping the new attribute. So what we are doing here is bringing convexity and multiply it with the x position of the points. So the x, because the head is in a higher value. So multiplying with x is gonna return a higher value for the new mask that we are creating. So I mix them both. I'm not multiplying it because mix them makes a cool has this cool option to have this bias. I mean, meaning which of these you want to multiply has a weight, a bigger weight for the mixing. And then finally I clamped the values to 0, 0, 1, because you don't want to have a mesh of 0 of size, because it's gonna get like super tiny and it's not gonna be useful. So again, basically I multiplied the convexity, I imported the vector of the convexity. Sorry, this should be a float. Should be a float. Yeah. I multiplied the convexity with the x value, and then I clamped it, and that's it. And then I got back this cool remesh mask. It's not returning anything. Yeah, maybe the values are too low to show here, but never mind. I am using remesh mask to get denser polygons on the back of the creature. And then with divide, you can compute these dual polygons, meaning you can get hexagons. Of course, denser hexagons in some areas. You can see like these beautiful patterns are being created, and it looks very nice on every area actually. Looks very nice how complex can mixing attributes can be. But this is what it returns, kind of a skin. And you can mix the skins, the hexagons. I mean, also I deleted anything that isn't hexagons. So so how can I group just the hexagons? Group expression, and then you come back, you come here in Bex expression, and you check 5-sided or greater, and you're grouping just the hexagons, right here, the hexagons. So I blasted the hexagons, and then I promoted this remesh mask from primitive to vertex. So what does this achieve? Because promoting the remesh mask to primitive to vertex allows us to have an attribute like kind of an ISO curve logic that you can start merging, sorry, splitting some vertex. But it's not showing here right away. It's going to show when you start extruding it. For example, when you extrude, you can check, you can see when you start extruding, you can see that some areas are being splitted. For example, I can vary this tolerance value and have another configuration of this kind of shells. You see, and all because of this remesh mask, which works as an ISO curve, so to say. So I extruded it and then smooth, and then that's all you need to get this kind of this skin. So you see that this is a very cool way of using attributes to drive models. Then I fused it. Then all the borders needed to be smoothed a bit and subdivided, and that makes this creature. That's all you need to make the creature. Of course, you can draw some claws on it or some I don't know. I mean, it's very infinite what you can achieve here. So I had a couple of more of experiments that I hope to show you guys. But before, for example, I wanted to show you guys also this animation that you can achieve on Houdini. It's pretty cool, but I don't think it's gonna be enough time to check this. But yeah, it's basically I also created here. What's more important here is the node, the created node. Yeah, it's over here. It's here, the radial symmetry node. So I created this asset. Maybe you can use it, guys, for your workflows, and that it achieves radial symmetry, because as far as I'm concerned, Houdini doesn't have this radial symmetry operator. So yeah, there are a lot of logics that are here that you can check. But as I told you first, I wanted to jump to Arnold. And let's see if we get time. Now open Maya. Yeah, also this I created this kind of habitat for you to check. Of course, it's all fully procedural as well, meaning meaning you can get different seats over here, for example, and it should work. Yeah, it should work. It's another habitat. It's pretty interesting. But yeah, you have the files there, guys, so you can also explore it on your own. So to open, after you open Maya, you have to just create a new scene. And let's start with the creation of this shader, okay? Because I'm gonna show you what this shader can do. I'm gonna show you. So check what can be done with Arnold. Oops. I think I have to close Houdini for this. Sadly, I think Zoom consumes a lot of GPU resources. So I have to close as much as I can. No. I don't know why Arnold is not letting me render right now. Just 1 second. Is this one? The GPU usage is pretty high. Well, before jumping there, I wanted to show you how to export this geometry to Maya. So what you have to do is basically save the geometry. You have to take your geometry here, right click it, save geometry, and you choose the folder or that better fits you, whatever you want. And also remember to use OBJ at the end. OBJ is pretty light, and it does hold UV textures, so it's pretty handy on that. So please save it whatever you want, and in OBJ preferably. So yeah, this is the OBJ. And I also wanted to create different maps, okay? We're gonna have different maps here. So one map is gonna be the measure curvature map, okay? Other map is gonna be the mask by feature. So we remember we use mask by feature. We're using the same logic here, but instead of the x vector, we're using the y vector. Like all the better match for this vector, the higher value and the mask is gonna have. Okay, So there is a mask created over here. Also, something that works for me a lot is remapping the colors of the mask or the colors of the curvatures to black and white, because this can hold values of from 0 to 1. It's up to you, but I suggest you to use this to map it to from 0 to 1. For example, I am mapping here the concavity color type ramp with the color node. I am mapping from ramp to attribute with the concavity, and here as well with the mask white feature. I am remapping the mask. That's cool. Okay. Then yeah, and then we have different maps. Okay, we have the geometry itself. We have the curvature. We have the mask. The mask that we created, which is like from this vector. And yeah, let's start with these 3 masks. Okay. Okay. To export the maps from Houdini, to bake them, we want to go to this image context. So remember, we are in the object context. So we want to go to the image context. Okay, so in this image context, we want to create image network. This image network node. Okay, if I jump in here in this image network node, I'm gonna get well, this is gonna be blank. Image is blank. So we wanna bring this Bob Cop2 generator. This is a node that will help us get this mask that we are checking over here. To check the mask, we're not gonna keep we're not gonna stay in the scene view, but we're gonna go to the composite view. Okay. In the composite view, we're gonna check the mask that that will allow that we will be allowed to export. So what do we need to connect this this node to the geometry that we're working with? First of all, we're gonna go to double check. We're gonna go I think we need to write a piece of code. Yeah. First, we need to check the size. Let me double check. Because here doesn't have a geo. Oh yes, we need to type in this Bob2Cop generator. Yeah, inside this Bob2Cop generator, we don't need this. We're gonna bring a parameter, and then we're gonna sorry, I always forget this word. So bring this snippet. We're gonna bring the parameter, and we're gonna bring this snippet, and we connect them. I mean, we can name the parameter however we want, but we're gonna use geo as a name and geo as a label, but geo with caps. So we can write this code. This piece of code is what helps us retrieve, what helps us get the data from the vice versa. It's what helps us get the data from any geometry. The maps. I'm gonna write the code here in case you guys wanna check. And remember, it's just jumping into Bob to generator and bringing the parameter and then bringing the snippet. And in the snippet, we're gonna get this data. Sorry, in the snippet, we're gonna write this code. And then in the geo, oh, sorry, something that I forgot is that this parameter shouldn't be a float. This parameter should be a string. Should be a string array, I think. No, shouldn't be string array, is geometry string. Yeah, sorry about it. It's a geometry string. A geometry string. Here it is. Cool. And now we can get any geometry we want. But the geometry that we want to work with, we need to write this text. Meaning, or we can even go here on this tab on the left, and you can search for your geometry. For example, I am looking precisely for the geometry called texture generator. So I just drag it here and I drop it. But it's not gonna drop with, yeah, I drop it here. So for it to work, we are missing as well this text, OP double points here. And that is how you get the color map from the mask, from the color we create. And we're having different maps here. This is a curvature map. We get the curvature map just by changing the geometry we're selecting. Because remember, this is like unfolding a UV map. Okay, so we're basically unfolding a UV map. So this is a color map, this is a curvature map, and this is the mask that we created, the personalized mask we created. So to export these maps, we need the ROP composition. Sorry, ROP file output, I think it's called. Yeah, ROP com. It's called ROP file output. This one. And you can well, you can check the folder here, search for and write the name you want, even in PNG, and then you render, and it's gonna render the image, this map. I don't know how high you can go on these sizes with Houdini Apprentice, but with Indie it doesn't have any limit. So I'm gonna close Houdini because I'm gonna with the maps exported. Here are my textures. I also created a displacement texture, but I want to close Houdini to check if it's better for Arnold. Hopefully it works right now. Yeah, it does work. The problem is that I had maybe I need a better GPU. It's yeah, it's an issue. Yeah, I'm gonna show you guys how to import all of that information from Houdini to Arnold. Okay. So basically, what you want to do here is import the geometry. Okay. And yeah. Well, first let's start from scratch because I think that I haven't shown anything about Maya. So let's open Maya again. So a very important recommendation that I want to give you guys is that please set a project because it helps you sort where you wanna save things. Okay. Set a folder for Maya. I literally saved the Maya folder for this workshop. So, and then you can create a new file. Okay. So this is the way you create a new file. In Maya, it's actually very similar to Houdini. But you have to use Alt to move to rotate. You rotate with the left click plus Alt, and to pan you pan with the middle button plus Alt, constantly clicking Alt. So yeah, that's the only difference. You have to click Alt and zoom in, zoom out with the scroll. Cool. So with the sphere exported, with our model exported, we just have to drop the model over here. Like you have the save model on in OBJ or in any other file type, and you just drag it and drop it here. And here is the model. Okay. Here is the model we create. Great. So this model doesn't contain any information on materials, by the way. So when you import from Houdini to Maya, this model doesn't contain any material information. Luckily, it does contain UV mapping, of course. So how do we start creating the material for this? We're gonna go to a hypersheet window. Just click on it. Just click on the hypersheet window, and this window is gonna show. So here, if you press tab, you can come to create an AI standard surface. And we're gonna name it shader. Okay. Just click on it. Just click here and name shader. I'm gonna do it again. Create AI standard surface. And I'm gonna name it shader. Okay. And then I can apply, I close the window, by the way. I can apply the material to this object. If I right click it, I click assign existing material, and I click on our new material created, shape. I'm gonna do it again. Right click, assign existing material, or shape. And yeah, we created a new material for our geometry, but we haven't applied any of the maps yet. To apply the maps on the material, what we're gonna do is just, again, drag and drop our created maps. We're gonna drop it on the hypersheet context, and we're gonna just, for example, this is texture 1 color. We're gonna just connect it to the base color node. Cool, it works. It doesn't show yet, but if we wanna look at the colors of the material, we have to jump on this option, texture. Just click on it, and colors are showing right now. Colors are showing. If we click on this other option over here, use all lights, it's gonna show dark because we don't have any light yet. So what we're gonna do is bring an area light. I'm gonna do it again. Arnold lights, area light. And with a W, we can access to this gumball and move the area light, okay? And just place it, and with the R, yeah, with the letter R on your keyboard, you can scale. So with W you move, and with R you scale. W R. So yeah, let's make this slide bigger so we don't get too funny with the composition. But there are a lot of composition ideas to apply to this kind of geometries. Yeah, this light is not showing. Remember, we have this option activated. It's not doing anything right now, the light, because it's in exposure 0. We can increase exposure of the light. We increase it to 12. It's gonna show a completely different shade. So let's create 2 lights. Let's not get too funny with this. Let's create lights. It's the most simple it's the most simple configuration that you're gonna get. One from the back and one from the front. That's cool. Yeah, and to create a camera on Arnold, because every rendering engine should use cameras, you go to create, you go to camera, and you create a camera, of course, here. Right now the camera is here, it's on the back. It's here. Camera's here. But if we wanna be more precise with the focusing point of the camera, we have to go to panels, to perspective, and go to camera 1. And then we can start, if you notice here, we're on the camera 1 visualization context. Okay, so we can focus on the object. Also, if you check on here on the resolution gate, you're gonna get this this frame where the camera is gonna focus. So for example, I wanna get a focus similar to this. Yeah, let's say. So we have to lock the camera before doing anything, because we already found our angle. We just click on lock camera, and yeah, that's all. We go to panels, we go to perspective, and we go to the perspective visualization, and that's the camera. We cannot do anything right now with the camera because it's locked. So yeah. Also, to start rendering with Arnold, there are some considerations. You have to go to Windows, and to go to rendering editors, render settings, and fix some configurations. For example, in the system, you do not want to render with the CPU, but with the GPU, because GPU is always going to be faster. And here in the Arnold render tab, I suggest you to change this to 10, which is like the samples that you're gonna get from the rendering. If you wanna get a higher render, you can always increase these settings. It's all about how precise the material you want to be, because something cool about Arnold is that it's physically based, so it always get like, and it's unbiased, so it always calculates like everything to create a most precise material. And that's it. Again, window rendering editors, render settings, and you just have to check on GPU and the camera. Cool. And yeah, we can start rendering. Also, something I almost forgot. In the rendering settings, sorry, in the render settings, you can also change the resolution of the render. Right now, it's in this preset, but you can change it to the 1K square. That's cool. You can also change the resolution, by the way, how many pixels you want per inch. Okay. And then to start rendering, you have to go to Arnold, open Arnold render view, and this window is going to show, and you have to click on play. And yeah, it's doing this because we haven't selected our camera yet. So you have to come here and select camera shape 1. And this is our piece being rendered. Also, something that I would suggest you guys to do is go to Window, to Display Settings, and not use the Arnold denoiser because it's kind of bad, honestly. I suggest you guys to use the denoiser optics. You can delete this. And that's it. So if we're not convinced with the angle, we can go to Panels, to Perspective, to Camera 1, and we unlock the camera. Have to unlock the camera. Unlock the camera. And zoom in the sphere. And you can see that it's being updated on here. And also, if you notice, this render is pretty fast because we already gave Arnold the information of the colors. So it's pretty cool because usually Arnold takes quite a while to process some stuff. I'm gonna show you guys in a few minutes some heavier operations that Arnold does. But yeah, and this is about color. And we can also introduce, for example, the curvature map into. I brought a curvature map here. If I connect it to the for example, curvature can be connected to curvature. Oops, it doesn't let me here. But if we can also convert this AI color to float, and this will give us values. This will give us the number of the colors. Yeah, basically converting the colors to numbers. So we can connect this to, for example, specular roughness, and we're gonna have less, less roughness on the curvature with less less concavity, I think. I do not like how this slide is what this slide is saying over here. But it's all because I can also modify color. I can just color correct over here. Color correct. And just color correct and maybe increase exposure. Increase the exposure of the mask. I'm increasing it like so. And full saturation, it doesn't have any saturation. The contrast I can also increase. To have this differentiation between these areas and these lower areas, right? To create some goo appearance. Also, I can come and apply this personalized mask that I created, and I can apply the. Just give me 1 second, guys. Sorry about that. And we can create a mask. We can bring the mask that we have created, and we can use this as an input for instance, we can start playing with the subsurface, um, with the subsurface. No, first maybe with coating. The coating can have coat color. Right now it's not doing anything, but can increase this. And for example, what this is doing is that it's creating a black coat on these areas, right? But it's creating a black coat on these areas and not on the mask. Yeah, because our mask is white on the top and dark on the bottom, right? So the white coat is being applied up and the dark coat is being applied on the downsides. It's a kind of interesting appearance, but we're losing a lot of color. So what we can do is again use color correct. Use color correct to tweak a bit this color. We're gonna tweak this color a bit. So we can add kind of even add some color on the coating. Maybe not green. We can add yellow. Yellow is kind of cool because gives appearance that it's kind of an infected organism. So that's just by adding this color, right? And the coating. The coating can also have some other interesting stuff like roughness. We increase the roughness a lot, and it's missing a lot of detail. Maybe 0.15. Yeah, and that's it from the masks. You can play a lot with these logics, and I sent you guys the files that I'm using. So, no, not this one, but the previous one that I shown, and you can check on it. I also wanted to review these other models, these other settings. Let's check on some other settings with another file. This tentacles is the model that we were working on earlier, but it's not. Yeah, these are the tentacles that we were working on earlier. And remember that we created this kind of creature from the mountains, from the mountain node, and yeah, we mapped the tentacles. Okay, I'm gonna close this. I'm gonna save as shaders just in case. And I want to show you guys how this, what's a result of this render. Okay, this render is much more complex, okay? So it has a lot of detail and it's a very complex tissue, as you can see. But I'm gonna show you guys the setting and the options that I added to the render to get this kind of render. because you can see that there is fog on the behind. There, the material is kind of is having this subsurface appearance over here, also here, and it also has some Fresnel effect facing yeah, that's it. Some depth of field as well. Yeah, let's check it by order. First of all, to achieve the depth of field, what you want to do is in the camera settings, you want to go to the Arnold tab. And in the Arnold tab, there is this option called enable depth of field. Okay. So, what's the right setting for this? Because the depth of field asks you, what depth of field is asking you to do is give a focus distance. This is pretty important. Where do you want the focus distance to be? So you want to first check what's the distance, for example, of the focus, right? We want to focus on this tentacle, for example. I am bringing, so for that, I'm going to have to bring a geometry, because here I can see the distance from the selected, from camera, sorry, distance from camera. For example, if I click this geometry, it says that the distance from camera is 10.55. But then it's a distance from the camera to the center of the object. So a little trick to work out, sorry, to activate this option, you have to go to display, heads up display, and activate the object details. Okay. Also, so yeah, so you have to create a sphere after activating the option and move it to wherever you want to focus. So this little trick, I scale it. This little trick helps us to get exactly where you want to focus. So the distance from camera is 6.05. So I wrote down here 6.05. Okay. I'm gonna go back to panels, perspective, camera. No, panels, perspective, and also I created this background. So so it reflects some lights better. It's always good to have this background. Yeah. Also lights. About lights, there are two type of lights here. Okay. These are the area lights that I have shown you guys to place before with Arnold lights, area light. But there are also these two other lights which are spotlights. What are the spotlights used for? There is a cool option in this. Well, actually, there are many options that are pretty different from the area lights. Like you can use a drop off, and you can have a cone angle for the aerial for the spotlight, because aerial light is just projecting rays like on all this area, right? And it's not maybe very sometimes might be better to use spotlight for these purposes. But also something that the spotlight has is that if we come here to the Arnold tab, you can activate the, sorry, no, it's not in the Arnold tab, I think. No, it's in the SideFX tab. You can activate the fog settings. Okay. You can activate the fog settings. And that's pretty cool because as I have shown you, there is a fog in the background. but this fog is coming from the lightning of this light that is coming from above, right? Like showing the hole in the creature. This light is what's projecting the fog. Well, not projecting, but interacting with the fog, But only this is not enough. What we need to do is come to Windows, to rendering. No, sorry. Yeah, Windows rendering editors, rendering settings, render settings, and in the Arnold renderer tab, we want to go to environment, and here it's the atmosphere setting, and here we can set an AI atmosphere volume. Sorry, we want to go to this checker tile and click on create AI atmosphere volume, and you create this volume. So the first thing that is gonna show, it's this one. So this density is pretty cool. I usually work with this, and also with color, you can do something very interesting, which is also go to the checker box on the color, and you can create an AI noise. And yeah, just click on the checker. And for example, I'm going to click on this one, and this window is going to show. You have to go to Arnold and create AI noise, and this is what's going to give a more natural fog, because you can see that the fog here is not uniform. It's like a noisy fog. So you want to go to the AI noise fog. No, sorry, to the color from the AI atmosphere volume. Click on the checker and select the AI noise. And here you can play around with the settings. Actually, I found these settings to be appropriate for this specific render, but you are gonna have to try a lot for your rendering. It's all about how it looks better, but it does. I think it does give the creature a lot of history, right? Sorry, a lot of story. Like maybe it's from the water, maybe it's from sulfur made environment. This creature is also does also have this um, bioluminescence, maybe. I don't know. But that's all about the setting. Let's jump into the material for this creature, because believe it or not, it's just one material that I applied here. Well, actually, a mix of two materials. Okay. You have, for mixing materials, for creating mixing materials, you have to create the mix shader, the AI mix shader. Okay. With the AI mix shader, you can combine two. I think you can even combine three materials, but I'm not sure. Never mind. You can combine two materials. Okay. I combined this material and this material. So in the hypershade context, we're gonna jump into this sphere. Let's check what this option does. Arnold. Let's check it. And it's not helping much. Maybe, yeah, it brings the shader ball here, but maybe I want to see if I can find another. No, it's not helping me very much. Well, there are many options here. You can check them. Because this material, I think, is not showing that good here. Never mind. Yeah, I think, yeah, I found my mistake. Yeah, I was not showing precisely because I was just clicking on this material, and this material is this, but tentacles are this, and mixed tentacles is this. So I shouldn't have used her, I think. Maybe it looks good on the cloth. Yeah, I think the cloth makes it really shine. Like, you can see as well here that it applies the second material only on the more convex areas, right? Here the second material is showing. This second material is showing, and mainly in the other materials, this is the material shown. So how do we mix these materials? First, I use an AI curvature node. So what this node does is that the same that we saw in Houdini. We can use a radio. Well, no, in Houdini we use multipliers, but here in Arnold we use radius and we use multiply mainly. Mainly those two are the ones that we need to modify. But also we are using a cell noise. And this helps us to create this kind of alligator noise, right? Like these geometric shapes. Also, I modified. I connected this cell noise to the bias because this is what's gonna mix better these two materials. Okay. Well, in this cell noise, I just modify the scale, and that's it. Also, additionally, this cell noise is going to be useful for us for bumps. So I connected the cell noise, the color to the bump map, to AI bump, and connected to the bump of the second material. And this is what helps to create these bumps only on the second material, but the first material remains the same. Does not have any bump. Just the second material has these bumps. We're gonna check better maybe in the current render, but that's all for the bumps. Well, tentacles are also very important because you can see here that well, the specular settings are not very important here, just the roughness and by the way, Arnold has some cool presets. Sorry, you can go to presets, go to skin, and go to replace. And what this achieves is that whenever you bring a material, you have like base settings. So, for example, if I'm gonna bring a new material, I'm gonna bring here a new material, and I wanna bring, for example, the skin material. And if you notice, it has this already skin-like appearance, like, and it helps as a starting point. Actually, I started this tentacle material with a skin material. What I tweaked is a lot of the subsurface colors and the subsurface scale. I didn't tweak the specular setting very much. Coating, just a bit of coating. But this is also a very cool shader. We can not only use mix shader to mix two materials, but we can use to combine two colors. And why do we need to combine two colors? Because there is this facing ratio node that it's related to the Fresnel effect. Hope you guys have heard about this at some point. But this Fresnel effect is this, like the borders of the facing areas of the geometry that's to the camera has one characteristic, and the node and the ones that are not facing the camera have another characteristic. So here's also another good effect of the Fresnel effect. It's mainly this. It's exactly what's happening here, but with this configuration. You wanna play with that, and you wanna bring as well two colors. I brought colors with the AI ABS node. So you bring two colors, you basically just check which colors you want, and you mix them on the mix shader with a facing ratio as the mix input. And yeah, but that's basically it. There is no much else to say here. And that's what achieves this cool rendering. You can start tweaking your materials as well. I've shared with you guys the configurations on this, so you can start tweaking the materials and check which colors you like better. Also, I created a material for the background because the background needed to be I needed the background to be blue to have a cool contrast with the creature. Also, to go back to the noise, to the fog, and the fog has these two colors, right? It also these two colors are also going to affect the background and the surroundings of the rendering. So pay attention to these colors of the fog, of the noise, sorry, that you're introducing to the atmosphere volume as well. So yeah, that's it. I don't know if you guys have any questions before closing the webinar, or maybe we can also increase these render settings so we can finish the webinar with a high quality render. Yeah.
Hey Cesar, said you were done?
Yes, yes. Unless there are any questions here on the chat, no. Yes. No.
Well, thank you. It was awesome webinar, very detailed and cool to dive into the visuals as well. It's always important.
Yes, yes. I wanted to show how to compose as well these kind of images that resemble natural and organic creatures. So it's pretty important.
Yeah, cool workflow between the different softwares, and yeah, it seems like everyone enjoyed it. So thank you everyone who stayed through the entire live webinar, and thank you Cesar for teaching it today on this Sunday.
I'm very glad to be here. I was very excited about this
Yeah,
webinar.
cool. Thank you, Walter. Okay, well, if there's no other questions, we'll end it here and let everyone enjoy the rest of their Sunday.
Great.
Okay. Until next time. See you.
Next time, guys. Bye.
Bye.